Okay. Think I actually hit my target time today, or I barely missed, one of the two. Um, but yeah, okay, here, let me ping my Discord real quick. Um, let's also put my face on real fast since I'm just doing little admin stuff I don't need anyone to see. Okay, so go here, grab the link, stream URL. Okay, boom. Does my link ever change? Wait, there's no way that's actually the link, right? That's like someone else's link, I think. Yeah, that's stupid. I'm sharing like the wrong link. Okay, I gotta figure out the share link. I should have both. Okay, that's embarrassing. If I read it, I would have known. That's tough. What's the? It should be on my dashboard, right? Um, let's see. Okay, I need to figure that out real quick. So, do any of y'all know if there's a link that I should be able to see? Like, maybe this? Got it. Okay. Okay, this makes way more sense. That's embarrassing. There we go. Now the actual link is there. Ooh, and there's a thumbnail too. That's nice. So what's up? What's up? I wonder what the latency is. I'm on low, so I bet that's a couple seconds. All right, let's get the other tab going. Was today? Yeah, interesting week, right? We had DeepSeek 4 or V4 come out, which I guess is cool. Um, any other like news type of stuff? Do y'all know off the top of your heads? Hey Hassan, or hey Hassan, what's up? Um, yeah, let's pull up the DeepSeek V4 and let me transition my scene real quick. Let's pull up DeepSeek V4. Let's see. I don't even remember. All I know is it's out actually. I guess they have a tech report, maybe? Okay, yeah, there's a tech report. There's a model card. There's already 100,000 downloads measured. I think that just includes half of one day, maybe. I don't know. We'll take a look though. Oops, let's go back to the tech report. I wonder, does this tech report get to be on Hugging Face papers? Like, or does it somehow not qualify or count? Oh, I guess it's this is just a README, so it doesn't count. Wait, is this where we were? This is where we were. Okay. Yeah, I guess this is just a PDF file. So you probably can't compute metrics against it anyway. Okay, sorry, let me pull up the chat. Yeah, a bunch of LLM releases this month. Who is 2. Oh, Kimi 2.6? Dang, the auto translate is dreadful. Let me it's automatically translating Kimi 2.6 to who is 2.6. I wonder what language Kimi means who is. Um, wait, was Kimi 2.6 this week though? I thought. Oh, was it this week? Yeah, time flies. Let me see. Can I see the release date somewhere? Oh yeah, that was totally this week. Cool. Cool, cool, cool. Um, and yeah, I guess it's okay. Well, this tech blog, is this focused on the model or mainly I don't know. I guess we can see. This is the tech report though, right? If this isn't the tech report, someone else feel free to send me the name or link to the actual tech report. But I think we've got both of these tech reports. Did I cover the paper neural computers? Doesn't sound familiar. Is it on Hugging Face, or if not, I can find wherever it is. This one, right? April 6th? I don't think I did. And to be fair, some of these weeks I've been mostly covering viewer papers. So if a viewer didn't, or like papers suggested by viewers. So if none of you asked for it, it probably wasn't covered. Yeah, we can look at this. Got some good upvotes too. Oh, it's a Schmidhuber paper. Interesting. How long has Schmidhuber been at KAUST for? Am I stupid? Wait, what? Did I know that? Has it just been forever and I just have never paid attention? When did he... Has it been forever and I'm just crazy? It's probably been forever and I'm just crazy. Let's see. This is a Schmidhuber paper. that I have in my head from a time when I should have been aware of where he was. And was he at KAUST then? Yeah, yeah, more or less. I mean, maybe I think of him more as like Swiss AI Lab, and maybe what's throwing me off is I always see Swiss AI Lab 2, and here I'm only seeing KAUST. So maybe that's what I'm thinking of. Is Jurgen the guy with the original World Models paper back in 2014? Probably. If you ask him, the answer is definitely yes. But maybe for real, yes. 2018, but yeah. Uh-huh. He was the last author on that one. Was this the original World Models paper? I feel like when he pointed this out, LeCun pointed out some older one, but I'm not sure. We can look at this quick too. It's a neat paper. I do remember reading it when, like a few years ago, when World Model popped up as a buzzword. A few years ago, like 2 years ago maybe. Everyone's like, what does this even mean? So like some people go to look at this paper, and now, how many position papers are there to read on World Model? I know there's this one too. Okay, this is gonna be hard to find because the name is like the name of a drug, right? No, it's not this one. It's this one. This is a world model position paper that I'm more familiar with. Does LeCun actually have a position paper, or does he just have JPA papers? Which, granted, JPA is his position, but like, did he write a paper staking that position or not? I'm not sure. Yeah, maybe we look at these for fun. I don't know. But for now, let's pull up some papers to look at that are recent. Okay, we can unsearch neural computers and take a look at some of the top stuff. Ooh, we talked about, no, we didn't talk about Tryon. I reviewed a Tryon paper. Okay, yeah, I want to look at Tryon. I want to look at state of the art because I'm kind of suspicious or skeptical of the Tryon paper that I reviewed and its quality. So let's look at what a state of the art Tryon paper this week looks like. Unified modeling. Ooh, with diffusion LLM. Okay, we can take a look at that. Uh, a language. What does that mean? I guess we'll look. One-step image generation. Okay, interested in that. Is that going to be diffusion at one step, or is this going to be like a diffusion's distilled to a GAN? Or I'm still waiting for someone. We still don't have. Do you all remember the drifting paper? Generative modeling via drifting, which is a Kaiming paper from recently that is single step. This is crazy. I just searched the title and I'm not getting the. Oh my goodness. Where's it's cited by 16? Where is it? Here it is. Okay. It was generation with one neural function evaluation, or like one forward. Are there any papers yet that use this to do text image? That's what I want to know. So I'm kind of just glancing through these really quickly through for text. We're not seeing text though, right? I can always like global search for text. I'm not seeing it. Text. Nope, nothing, right? Okay, because I'm kind of waiting for that. That paper seemed cool. Unless there's something like crazy wrong with the method, it seems like you could probably use it for text image, which means we'd see someone use that for single step image generation. Anyway, let's one step latent reasoning and planning with vision language explanation. Sure. If it was just one step reasoning and planning, but I'm wondering what they mean when they say latent. Latent planning and explanation. Real quick, I'm gonna go through with my OBS and I'm going to check to make sure that I have these papers at like the right width in case I want to clip it for a short later. The answer so far is okay, that's good for that one. For this one, I could go a little bigger. I'll just keep it though. For this one, it's 85. I recognize that template. That's the same width as the CVPR. I don't know if it is CVPR, but that's how wide CVPR is. For this one, let's just go to 90 to be safe, yeah. And for this one, let's go to 90. Boom. Okay, cool. We got those. Oh, let's make sure. Okay, so for this tech report, let's download it, I guess. Because then we can like look at it in our PDF viewer. And I just closed it. Okay. Let's take a look. So 90 maybe? Nah, that's too small. 95. Beautiful. Okay. This one, do we have a PDF here, or is it really just the blog? It's just the blog, right? Okay. So I can't, unfortunately, resize it, but that's okay. We'll go through that one maybe first. And in case we do want to talk about this, let's just do my resize so I don't forget. And the size for this is already good. Okay, cool. Maybe we'll go through this first since it's our only non-PDF. I don't even think I want to go through it with the timer. We'll just see what details they do share. First time seeing a Xiaomi paper. Is it you only? The name sounds vaguely familiar, but I'm not sure. Where's a good way to see this? Like, yeah, how would I actually judge whether it's my first time seeing it or not? I guess maybe here, like we can go to this. Oh, we need to open it on its own tab. And that ruined my resize. Hold on, sorry. Technical difficulties, eh? Okay, bada bing, bada boom. This time open on its own tab. We can look at the website and maybe like, let's go to the Hugging Face. Oh, we were already there. Here, oh, we can just, there we go, that's what I wanted. Apparently they did some multilingual stuff with, actually, I don't know if this is based on Google's Gemma or not, but maybe it is, probably. So a few machine translation things, and this is text to speech, right? So some machine translation, some text to speech. And what about papers? This one? This one? Okay, so we get this planning one. We get this vision language action model. And we get this video streaming thinking. Interesting thing about this to me is this one is embodied intelligence, which I would think of embodied intelligence typically as like robots, right? This one is Xiaomi Robotics. Are these like competing teams? And then this one is an intern paper, right? I mean, yeah, at the university, so I'd assume. Yeah, co-first authors both at the university. These probably aren't the only papers they've ever done, but I feel like we reviewed this one on the stream. I don't remember though. These probably aren't the only papers they've ever done, but they do seem to be the only ones that they bothered to listen to Hugging Face, and they're all from the past couple months. So I think you're onto something, Hassan. Maybe they're kind of newer. And to be clear, they might not even be very large, right? Like, it might just be that they happened to start things up a few months ago, and their embodied AI team and their robotics team had papers ready within a month of each other. That kind of makes sense. Although if you start seeing a flood of stuff from them, well, then we know, right? Okay, Kimi K. Okay, so let's look at this real quick. New Kimi model, open sourcing their latest. Oh, open sourcing it. So I can go download the weights somewhere? Is that how I got here in the first place? Where does this, okay, if I go to Kimi.com, they're saying that's now available via Kimi.com, the Kimi app, the API, and Kimi code. Okay, well this is just interacting with it in chat. Where can I get, like... Oh, we literally came from this, didn't we? Okay. Oh, that's a lot of downloads, but I guess it's been a couple days. Okay, so it's open sourced, which we knew because that's how I got there. I just forgot. Man, these, okay. I took a data viz class during grad school, and one thing they would talk about is like the key thing that you want to think about when you're thinking of your visualizations is just when you want people to be able to tell a difference between things, can they tell a difference? And the awkward part about something like this is there actually are differences between these. I can't see them though. Like 54 is bigger than 53, but the bars are basically the same height. Uh, that can benefit you sometimes. So that's a bummer when you are the best on that thing. Uh, However, it helps you when you're not the best because then your 83.2 looks kind of like their 83.7, even though it's not, right? What is the y-axis in this case? Is it just 0? No, because this 83.2 is barely bigger than 54. How did they choose the y-axis for these? Anyway, I'm not a fan of the plots, but let's keep looking. So this is just kind of, I almost think of this at this point as like benchmark slop, like cool, we see lots of bars. Yeah, they're basically the same size as the other bars. I was mainly here to see if they say what they like changed. So they say improvements in long horizon coding tasks. Do they say anything about how? Okay, they download and deployed Qwen 3.5.8b locally. Oh, so the complex engineering task was to optimize inference for this small Qwen model in Zig, and it improved the throughput from 15 tokens per second to 183 tokens per second. Cool. That's a well constrained but interesting engineering task, and it's nice to think you could do such a thing with your coding agent, right? Tell it, hey, grab this model, take this language, just keep iterating until you speed the model up quite a bit. This is kind of reminiscent too of like the Carpathia auto research plot, right? Okay. Autonomously overhauled exchange core. Okay, so like more like complex tasks. And this is interesting to me because these are case studies, right? This one is like optimize the Qwen 3.5 in Zig. This one is overhaul exchange core to increase the throughput. Cool. That's kind of neat. I like that. Like instead of just, I did just call this benchmark slop. It is nice to just see some like case study stuff. Granted, those heavily cherry picked probably. Like you could try to have it do 20 tasks and it could fail in 18 and then you just do case studies on the two where it worked. They're not really saying anything about the method though, are they? Let's see. Okay, these are more, these are like testimonials, which is interesting, showing up before maybe even the technical detail they want to share. Turn single prompts into complete front-end interfaces, expand beyond. We established oh, they have their own benchmark, huh? And they do really well on their internal benchmark. Interesting. It is important to be careful about this. If Kimmy's actually better, it's fine that they went on their internal benchmark. It would certainly be very dangerous that you happen to define a benchmark that you then kind of internally benchmarks on, and maybe it doesn't represent the world as well as you wish it did. Oh, there's also autokernel. Okay, yeah, we'll check out autokernel in a second. I don't think we're gonna find um any actual technical detail. Like we'll get numbers, right? Like this is the scale of the agent swarm. 300 subagents, 4,000 coordinate steps. Um, but that's not like how. Proactive, bring your own agents. Yeah, I don't think, sorry guys, I don't think we're getting any actual technical detail. But that's fine. Maybe they'll come out with something later. They do publish quite a bit. Um, like, did the last technical report come out at the same time as the model? I don't know. We can check another time. Okay, let's take a look at this autokernel, which is like a follow-up to auto research. Is it this? Am I in the right place? Auto research for GPU kernels? Oh, okay. Did I see this? I don't remember. Give it any PyTorch model, it'll profile the model to find which GPU kernels have bottlenecks, extract each bottleneck, optimize each kernel autonomously, and verify intent correctness. That's sweet. That's pretty neat. What kind of speedups do you get from that? Do they give any as examples? How do they do on kernel bench? Is there like a... Okay, no, there's not a paper. The README is what we're going to get. Okay, so I'll stop scrolling like a maniac. Profile, extract, orchestrate, bench, verify. Nice. And then I assume you loop these, right? Oh, these are the kernels they'll optimize for you. Okay. The Matmul, the Softmax, Layer Norm, RMS Norm, Flash Attention, Fused MLP, Cross Entropy, Rotary Embedding, and Reduce. Nice. Do they give any like numbers anywhere? Do y'all know? There's a paper? Oh, sick. Here, I did see something. Could it be this? This seems right. Let's see. It was right now AI? Yep, this is it. Okay. Yeah, let's see what the speed ups are real quick. How fast can this make your stuff? Feels like the big difference between the stuff that's working now and the stuff that was like pretending to work a year or 2 years ago is mainly that they get the verification right. Because then the model can't lie to you that it sped up your thing when actually it totally just destroyed itself. Okay, let's see. Um, Kernel performance, 3 baselines. PyTorch Eager, the slowest. Compile, which is the max auto tune, and then their. Okay. Okay, I'm super confused by this part. Anyone else super confused by this part? Just at the top? How did you get slower? Um, how did you get slower than Eager? I guess by not using it as a starting point at all? I guess that's fair. Um, if your matmulls are slower, is your model faster? Is that not where most of your time is? Is in the matmulls in your attention and then the matmulls in your forward? Isn't that most of the time in a or is this like a table where they do they normally start from the initial implementation then speed that up? This is just the table where they try to show what if we started from nothing? And so in reality they do get decent speed ups. I mean I don't see like results, right? It's just that comparison to the torch.compile. Okay, so I guess it's still got a ways to go, right? Um, it's a neat idea, but kernels are hard, and doing them with no human in the loop is a pain. I mean, I do know, like, I have coworkers that use these tools to write their own kernels, and uh, even the top GPT and Claude stuff just makes tons and tons and tons of mistakes that are very tricky to find, but that you have to fix. Otherwise, your implementation is beyond the implementation not being fast enough. The bigger issues are that the implementation will either be wrong, or it'll just be like very prone to crash in ways that are super duper hard to diagnose. Um, because we're not kernel engineers, right? We're just people using AI to pretend to be kernel engineers. Anyway, interesting. All right, let's get back to your regularly scheduled programming. All right, so we got some of these papers open. We kind of start going through stuff. I know, Hassan, you asked about neural computers. We'll do that right now. DeepSeek V4 is new. Let's grab that. Let's put that there as like a place, like a bookmark kind of. Okay. Well, I guess everything's new. I shouldn't have said DeepSeek V4 is new. I should have said DeepSeek V4 is very different structure to the other stuff we do. In fact, let's just do it first. I'm not even going to set a timer for this because I'm not setting timers for like 55-page technical reports. That just feels a little bit silly. Um, Man, I don't want to spend forever on this either. So let's try to see if we can quickly identify what the interesting things are going to be. Key upgrades are an architecture that combines compressed sparse attention and heavily compressed attention to improve the long context efficiency, manifold constrained hyperconnections that enhance conventional residual connections, and the muon optimizer for, oh, is this their fast time using muon? Is this their first time using muon? I want to go there right now. I want to see what their muon recipe is. Let's go check out their muon recipe. Do they use only muon? Do they still use AtomW for like embeddings and stuff? How do they sync up the learning rates and stuff? Let's see. Um, Okay. They maintain the AtomW optimizer for the embedding module, the prediction head module, and the static biases and gating factors. Okay. So that's very similar to the recipe that everyone's been using. Following Leo et al., we also apply weight decay to mu1 parameters. Yep. Use the Nesterov. Yep. Rescale the root mean square of the update matrix for reutilization of our AtomW hyperparameters. Different from them, we use hybrid Newton-Schultz iterations for orthogonalization, which is for a given matrix M, let its singular value decomposition be, the Newton-Schultz iterations aim to approximately orthogonalize M to be UV transpose T. Usually M will first be normalized, okay, to ensure its maximum singular value does not exceed 1. Then each Newton-Schultz iteration performs the following operation. Our hybrid Newton-Schultz performs 10 iterations over 2 distinct stages. During the first 10 steps, we use coefficients to drive rapid convergence, bring the singular values close to 1. In the final 2 steps, we switch to these convergence. Okay, wait. Is this something I should just know about? Have people been doing this hybrid Newton-Schultz optimization with other optimizers? Because there's so many coefficients chosen and like hyperparameters, like iterations, and I don't know where they come from. And I also don't have a great feel intuitively for how long this would take, right? We run SVD on M. So we run SVD on the momentum buffer plus the gradients. Okay, so that sounds like it's not, I mean, I guess that's not the most expensive part, but then we're like summing this result a lot. I guess that's cheap too. No, except that this is a multiply. That's not super cheap, right? Am I missing something? This seems like it would be kind of expensive to do in 10 iterations. Unless I'm going crazy. Unless is this M actually the UV transpose T? And that's what they were trying to say when they say like, I get that they're obviously saying they approximately orthogonalize M, right? What I mean is like, when do they use that approximately orthogonalized M here? In which case that's how it's fast, right? Do I have an intuition for why they do that? Not really. What would that accomplish? Just better orthogonalization, I guess. Interesting, but still, same responsibilities on AtomW. Still, root mean square for reutilizing with the AtomW hyperparameters. I am curious if they end up tuning those learning rates separately at all, though. So I'm going to keep looking until they maybe. I'll see how much they give me. Do they give me a learning rate? Do they give me anything else? Hello from Greece. Hey, NT0. Team Unsloth does some good stuff in kernels. If you want me to look at the paper, Hassan, feel free to share it. I feel like Team Unsloth is the one. Is that the team? Okay. I shouldn't leave this paper, but I'm still thinking about it. Team Unsloth. That might be the team I'm thinking of that kind of faked everyone out a couple years ago. But that might be a different one too. I don't know. Yeah, I'm thinking of something else. Never mind. Yeah, if you see a paper from them that you want me to go over, Hassan, feel free to post it. Okay, I wanted to see that. Okay, so the mu1 optimizer, full gradient matrix was a challenge combined with zero redundancy optimizer. Okay. Oh, so they're not going to give me what I want here, right? Not really. This is kind of like not a hardware detail, but not the detail that I'm looking for. Yeah, mu1 for, okay, here we go. For AtomW, we set the betas, the epsilon. Ooh, that's a really low epsilon. And a weight decay. Let's see. Okay, same weight decay. They don't, so this is something I've been thinking about. Like, should AtomW and mu1 share a weight decay? It seems like theoretically no, but it seems like in practice we're always setting them to the same value. And this is like a very standard value, by the way. 0.1 for mu1 is like what I see pretty much everywhere, except for diffusion folks for some reason seem to be picking lower values. I'm not sure if they're doing that for good reason, because the thing is, if you do your weight decay sweeps in a low step regime, but like the same model size, the same data size, you'll just get a better result from lower weight decay. the higher weight decay should beat your lower weight decay on some crossover point after like quite a lot of training. So I'm kind of skeptical of the values that I see a lot of the diffusion models picking, because I'm not sure why you would want a value lower than 0.1, because it just makes your parameters get so huge. But anyway, maybe that's not a bad thing. I think I still don't quite understand fully the impact of a very, very like high norm model, especially when we're normalizing pretty much everything that comes out of it, which is, well, let's get to be so high norm in the first place. But anyway, okay, so right now, based on what I'm seeing here, oh, that's a little different. That's a different value. I mean, granted, their update matrix is computed a little differently than the prior works, right? Yeah, because their update matrix comes from a different orthogonalization, so maybe the scale is a bit different. But 0.18 is not the standard value. So that's a change, I guess. I wonder if they tuned that. The idea of having to tune that hyperparameter is a little scary. But this lets you continue to use the same learning rate, which is nice. So they do linear warm-up for 2K steps, keep it for most of training, and then they decay. I would guess it's the last 10% of steps or something, but it could be even less. But they don't decay to 0. They actually just decay down one order of magnitude, which I think just keeps the model in a better condition to be ready for like mid-train, post-train, whatever. Okay. What else did I want to see? So I thought it was neat that they'd start using Mu1, and I wanted to see that. We saw that. I wanted to see what their fancy skip connection is, and this attention implementation as well. So let's go look for those. And I don't really care about the results as much. Okay, so core architectures of CSA. It compresses the number of KV entries to 1 over m times, and then applies DeepSeek sparse attention for further acceleration. Additionally, a small set of sliding window KV entries is combined with the selected compressed KV entries to enhance local fine-grained dependencies. Okay, so hidden state of KV tokens and the hidden state of the query token. We get queries and compressed indexer queries. I want to see the details of that a little bit more. But we're going to take the hidden state KV tokens, pass them through a token level compressor. Okay, see, that's the weird part to me. We're showing here the token level compressor that gets our compressed indexer keys. But we're going to do some multi-query attention on these compressed representations, get some index scores. This is called a lightning indexer, because what it looks like here now is not only have we compressed, like made the dim smaller, we've even selected fewer of our hidden states to be the compressed indexer keys. Okay, we'll look at that more. Okay, so multi-query attention gives these index scores. These index scores help us. Okay, so it looks like this token level compressor does not have as strict of compression as this one. It still looks like we're merging or pruning KV entries, or maybe, no, this is the sliding window. So sliding window here, some kind of compression both this way and this way here. Goes into a top K selector, select some compressed KV entries. Okay, so in this case, we're not changing the dim, we're just selecting them to where, I wonder if they're always supposed to match? Like our sliding window size is always the compressed size? Because it shouldn't matter, right? Because then we just concatenate them and do a shared key value multi-query attention on like a medium compressed query. And this is the weird part to me. How do we get the query token compressed at both these levels? Are we just not showing these to not take up space? I would assume that, right? It's probably the same token level compressor. Okay, so hybrid attention with CSA and HCA. As the context length reaches extreme scale, attention mechanism is the dominant computational bottleneck. So they designed the CSA, the compressed sparse attention which we just looked at, and they also designed the heavily compressed attention and employ their interleaved hybrid configuration. What is their interleaved hybrid configuration? Okay, so do we have a diagram of the HCA maybe on the next page? Yeah, okay. So heavier compression. We have a token level compressor, which looks like it somehow reduces the number of tokens and also cuts their dimension by a lot. We also have the same sliding window as before. We concatenate, and then we do the shared key value multi-query attention. Okay, so heavily compressed attention seems to be compressed sparse attention, but without the lightning indexer, and merging the top case selector with a token level compressor that gives the same number of tokens as we would get from the top case selector. So it reduces these two steps to one, removes this part completely. That seems to be the difference. So I guess it's faster. So I guess when they say that they have a hybrid configuration, does that just mean sometimes we're going to route to the HCA and sometimes to the CSA? Or how is that going to work? Let's see if we can see what their interleaved hybrid configuration is. Okay, so CSA compresses the key value cache of every M tokens into one entry, and then apply where every token can, and then HCA aims for extreme compression by consolidating. Okay, yep. The hybrid architecture remains, the hybrid architecture remarkably improves the long context efficiency, making 1 million token context feasible in practice. Okay, I still want to see the hybrid configuration. I don't really care to see other details. I think if they don't make sense, they're like one step away from making sense. I mainly want to know how we're interleaving these, right? Our hybrid attention incorporates several other techniques. For writing clearly, we omit them. I don't feel like that makes the writing clearer. Oh, they describe them here though. Okay. These are just, yeah, attention sync. That's pretty standard. It's just a trick to set a series of learnable sync logits. And for the the attention head, you add the exponent to the denominator of the attention score, which allows each query head to adjust its total attention scores to not equal to 1 or to even be near 0. That's fine. Additional branch of sliding window attention to preserve causality. Each query attends to only preceding compressed KV blocks. Consequently, a query can access information from other tokens within its own. Oh, what? Oh, I guess because the compression is almost like, oh, maybe we do need to look closer how they do the compression. I think what they're saying is like you could have like maybe information within your compressed sequence isn't like ordered the way it should have been anymore. Is that what it can mean? That doesn't make sense. But yeah, it says each query attends to only preceding compressed KV blocks. So a query cannot access information from other tokens within its own compressed block. But recent tokens are pretty relevant. So they have a supplementary attention branch in a sliding window manner. For each query token, we additionally produce some uncompressed KV entries corresponding to recent tokens. So they basically do like a regular sliding window attention as well. I still want to know more detail about this interleaving though. Like what is maybe I shouldn't care about the interleaving. Maybe that's the moral of the story here. But I do care. I want to know if we're just like alternating between them on different steps or using them for some portion of query tokens, because that should be possible as well, right? Well, that's the same as what I just said. Never mind. What is the interleaving? I don't think we get to see it. Hybrid representation. No. Third relative. No. Yeah, I still don't. Darn. And we're done with the section now. Okay, that's fine. Do I feel like seeing more details of the token level compressor? Kind of feel like, are they going to tell me the intuition for the lightning indexer a little more? After obtaining compressed KV entries, CSA applies the DSA strategy to select top K compressed CV entries for core attention. First, same compression operation to get compressed indexer keys where there's some indexer head dimension. Then for a query token, we produce the indexer queries in a low rank manner. Where do we get this weight matrix from? Or, oh, they're telling us here. Okay, sorry. Where I should have read down, not up. The input hidden state of the query token, the compressed latent vector for queries, the query compression dimension, and the number of indexer query heads. The down projection and up projection matrices for indexer queries respectively. Wait, when do we up project? When does that happen? Where do we ever up project? see a lot of down projection. I've never seen up projection though. Oh, is that just the DSA strategy and I'm just not remembering off the top of my head what the DeepSeek sparse attention strategy is? It's always just this compress and then this upscale. That's probably what it is, right? Then you compute the index score, or is it just that like the dimension, like these are still low dim, I guess, right? Because I think this is still, I mean, we're talking about the lightning indexer, so this is to give us these like really tiny dim tokens. The index score between the query token and preceding compressed block is computed by where this right here is a learnable matrix, and each weight is the weight of the sum indexer head, and then a top case selector to selectively retain a subset of compressed KV entries for subsequent core attention. And that's all. See, okay. One thing I feel like the more time I spend in this section is, and this is how I feel in general when I read stuff like this, is I'm almost like shooting myself in the foot by being here instead of trying to look at the implementation in code. Man, this is where like I could really embarrass myself though, because I don't read a ton of LLM model code. Although with diffusion and our large diffusion models, we're often just copying the way that they do things, right? So I am going to just look, and maybe things will become a little bit more clear in the code. I see their attention. I want to see where it's called. I need to see where it's initialized, and I need to see where it's called. Here's where they construct blocks. Ooh, we can also just see their hyperconnection mixing just in the code. That might make it a little easier, right? Okay, so they're going to initialize some attention. They have their MOEFF feed forward blocks, RMS norm, some scalar, right? That's what I assume this is for their hyperconnection molt, and then hyperconnection sinkhorn emitters. Oh, maybe that would have been more clear in the paper. It's okay. We can go back if we need to. And then there's some epsilon that we're going to need for this hyperconnection, and some dim. Oh, wait, what? Oh, this scalar dictates like some dimension expansion for our hyperconnection. Okay, I'm really curious to see how that looks in the forward. Oh, and it's fancy. Okay, so within our forward, we start with X, and we are going to first compute a hyperconnection pre, and then norm, and then attention, and then we're going to do the HC post. So for attention, we have both an HC pre and an HC post, and what you notice is we don't have the standard skip connection, right? Like the X plus equals. I assume that's handled right here in the HC post, so we'll look at that. Same thing for the MOE feed forward, right? We have the norm in the feed forward, but instead of the like standard skip connection, we have this HC pre and this HC post. How do those work? So it's true. I could use that would require setting it up on my personal machine. Believe it or not, on this computer, I have like no development tool set up at all. I use this for gaming and streaming, and that is it. My work stuff is totally constrained to my work computer. But yeah, if we're going to go through code more, I should definitely set it up. I kind of like it this way though. With something this simple, I feel like I'm about to get punished hunting for the attention. But this is like 10 lines of code. I'd almost prefer to just use my eyes on this one. But yeah, the attention is going to probably become pretty punishing. Well, and then I'm going to hit stuff like the HC split sinkhorn, and we're going to have to jump to something else, right? Let's try to see at least where the residual connection was placed, right? Which seems to be here probably, right? Okay, well, actually, okay, so this, I suppose, is a clone. So this is the residual that we're supposed to track. We also get this post and this comb. And we're going to do something with all of them, right? But like, let's track the residual first. And the residual does not go into the pre at all, right? No, it only goes into the post. Okay, so we are going to take the residual and do, can we at least, if they had GitHub, I could at least highlight stuff. This is kind of crazy going through it in plain text, but it's fine. We'll rock with it for now. I think your idea, Hassan, though, for getting my AI IDE set up here for this would be nice. Another time though. Let's just focus on this, and I'll answer your gaming question in a second. Okay, so we got the residual, and okay, so this is essentially our standard residual connection, right? Except we are multiplying our actual x by some comb. So instead of x plus equals ffn, already we have x times equals some comb plus, sorry, I mean, I can't even express it that way. Like, because it's, we're basically modifying the residual before we add it to the result of what just happened. So that makes, okay, so post, so it's multiplication on both ends. Post is a thing to multiply by x, which is the result of our attention or the result of our feed forward. And comb is something to multiply by our residual, our old x. Okay, how do we compute those then? And what would be the intuition for that? That's weird. That you know, if we just remove comb, it's almost sort of normal, right? Like if we remove comb, then it's x plus equals post times ffn, or post times attention. But it's not. The thing that really makes this weird and different is comb. We also have something very similar in that this is pre is like post, right? Pre is like, we could almost represent pre in terms of a standard skip connection. Comb is what really breaks this and makes it not standard skip connection. But pre is just another way that we rescale x. For now, I'm going to assume element wise. But remember, we had that HC scale and we have our HC dim, which is bigger than our actual dim. And so let's look at this HC pre now and figure out how we compute this pre, this post, and this comb, all of which are multiplied by x in a way that appears to be element-wise, but at different stages. Okay, so we first get, okay, this is going to be really stupid of me, but what is this function? Oh, it's the reciprocal of the square root. That's handy. I have definitely written 1 over square root before, instead of just this. Okay, so the reciprocal of the square root of, sorry, more torch functions I should obviously know, but don't. Is this, oh my god. Is this just torch.pow 2? Huh. The more you know. Is it faster, I guess? Yeah, it's more memory efficient. Okay. Interesting. I've always written it one of several other ways. Okay. So we take x squared. We take, okay. So we keep, wait a second. Does this, no, it still means when we keep the dim, we just keep we keep that dim, but it's going to be of length 1 because we just took a mean along it, right? And we took a mean along the last dim of x, which means we took a mean along the hidden dimension, right? Okay. So we took a mean along the hidden dimension. So we basically took a mean on every token, and then we square x, and then we take the reciprocal of the square root. Sorry, we square x, we take the mean. So it's almost as if we did 1 over x, except we didn't because we did the square before the mean. Okay. Some epsilon just to allow for numerical stability since we're taking 1 over. You know, we don't want to divide by 0, but that's nothing significant. Then we have this linear projection using our HCFN, which, where did we initialize HCFN? Where did that come from? HCFN. Okay, we have 2 different HCFNs. Okay, So we have an HCFN for the attention, we have HCFN separately for the feed forward, and it's going to be something of shape mix HC, HC dim. By the way, I did notice that in X's shape, we already have HC, so it seems like what's happening here is we've already changed the shape of X according to whatever the HC dim is. This is the sequence length, right? So this is the sequence length, and then this isn't actually the original token dim. I guess this is weird. So this is the dim of a block, but the token dim, I suppose, would be HC dim times dim. This is like, I expected this to be smaller in terms of changing the architecture, but it actually seems pretty significant as a change to the architecture. We'll go look at the model for it in a second and see exactly how they're changing X, or actually that's probably what we should go look at now, huh? Okay, let's go look at that now. We have, I mean, I feel like I'm still misunderstanding something. Because we still just have args.dim and the HC dim is just strictly, dim times something else, right? In the forward itself, we get our input IDs, we embed them, we unsqueeze them, and then we make copies for the hyperconnections. Oh. Wait, how computationally expensive is this then? Okay, so it's actually, we're repeating it. So we have the same token dim, we've just repeated it. So at the start of the network, we're just going to have duplicates, right? The first block is going to deal with all these duplicates. It's just been repeated. But very quickly, those are going to diverge from each other, right? And does that mean that, like, if I call myself .head, actually I should look at the head, right? Is the head its own block? Parallel head. I assume this head has to simplify our dimensions again, right? I kind of don't want to look at that part right now. So I'll leave some of this to you if you want to come look at details later. I mainly want to finish understanding this. Okay, so X, unlike my assumption, X is actually already much larger than it would have been, where in the first block, this HC is where we just repeated it, but then later I assume that ends up being like fairly unique, right? But yeah, the shape of Y, like we're always preserving this HC. Block doesn't, make HC go away. Okay, so basically for every single HC dim, we have averaged along dim. So this actually becomes cheap, right? Because HC probably isn't that big. That would be crazy. So for however many like hyperconnection dims we've chosen, we average the square of all tokens and then take 1 over the square root, which would end up being smaller when the values for a given token tend to be larger, right? And it would be larger wherever the values for the given token tend to be smaller. So does it operate as like a smoothing? Let's see how it's used. Yeah, it's like a way to sort of normalize to control for like higher magnitude tokens. Because then we just have this linear, right, with X and with their HCFN, where HCFN is going to, okay, so it's going to take an X, which is BSHCD, and multiply it by a matrix of shape. Wait, what is mixHC? MixHC is 2 plus HC mult times HC mult. Okay, so it's something, hold on, smaller, right, than the HC dim? Because the HC dim, so both of them are HC mult times, but one of them is 2 plus the HC, oh, no, it's, yeah, smaller. It's definitely small, unless HC mult is, like, pretty close to the size of dim, which there's no way it is. This ends up being pretty small. So what's the effect on the shape here? The thing that they have in common is the HC dim, and so we're changing that basically. We're basically projecting it down to some mix HC size, and then we're smoothing it to control for high magnitude tokens, and then what are we doing with those mixes? So we have mixes, we have our HC scale, which is this, right? which is still throwing me off, by the way, but that's what that is. Right? That's all that was. Self dot. Oh, no, sorry. This HC scale is this. Okay. So which is how can that be three-dimensional? I guess if I look at the HC split sinkhorn, maybe I'll understand how it can be three-dimensional. Maybe there's just somehow always three components in that implementation. And we're going to pass in our HC base, which is 1 per HC dim. And then however many iters, which we read in the paper, that ends up being... No, we didn't read this part in the paper, so we just don't know. We could go back to the paper to figure out hyperparameters. Okay. Let's go see how this works. Oh, it's going to be in kernel code. Maybe we'll go back to the paper to see how that works. Okay, we're going to get some pre, post, and comp from it. The pre is something to multiply x by now. The post is something to multiply x by after. And the comp is something to multiply the residual by before we do the addition. Okay. Feel like I learned quite a bit about how this works. I didn't learn more about the attention, which is not why I came there for, but at this point I've spent way longer than I felt like spending on this paper. So y'all can do a deeper dive on the attention later if you want to. I am going to... How do you even come up with this stuff is a great point. That's part of what I want to figure out with this one little thing, is if I can kind of understand vaguely what the intuition would be for changing this. And maybe they'll explain that in the part of the paper that describes it, which is this. And yeah, and NT-Xeris, the good thing with DeepSeek is that it's open source. Exactly. This kind of makes you wonder if, how many tricks are built into GPT at this point? Like, some of this stuff seems crazy complicated, but maybe there's like a really good reason to do it. Okay. So we want to strengthen the conventional residual connections between adjacent transformer blocks. The idea is to constrain the residual mapping onto a specific manifold, and thus enhance the stability of signal propagation across layers while preserving model expressivity. This subsection briefly introduces the standard HC. Okay. So the standard HC expands the width of the residual stream by a factor of n. Yeah, we just saw that. It's just a repeat. And the shape of the residual stream is expanded where D is the hidden size of the actual layer input. Yes, we saw that. Let X be the residual state before the nth layer. HC introduces 3 linear mappings: an input mapping, a residual transformation, and an output mapping. The update of the residual state is then formulated as some transformation on the residual state plus some transformation on like the feed forward output, on some transformation on what? What is X again? Oh, X is the residual state. A is the input mapping. Note that the actual layer input, is also d-dimensional, so the expanded residual width does not influence the design of the inner layers. HC decouples the residual width from the actual hidden size. Offering a complementary scaling axis with minimal computational overhead, as NHC is typically much smaller than hidden size D. Yeah. So the mean that we do there is going to save computation on this stage. However, even though HC has demonstrated potential in improving model performance, we find that the training will frequently exhibit numerical instability when stacking multiple layers, which hinders the scaling of HC. The core innovation of MHC is to constrain the residual mapping matrix B to the manifold of doubly stochastic matrices, the Birkhoff polytype, M, and thus enhance the stability of signal propagation across layers. This constraint ensures that the spectral norm of the mapping matrix is bounded by 1. Oh. So, okay. This is giving me some guesses at where they would have come up with this. But let's keep reading and then I'll say my guesses. The residual transformation is not expansive, which increases the numerical stability both during the forward, passing, and back propagation. Besides, the set M is closed under multiplication, which guarantees stability in the scenarios of deep stacks of MHC. In addition, the input transformation A and output transformation C are also constrained to be non-negative and bounded via a sigmoid function to avoid the risk of signal cancellation. Okay. Right, we would need to avoid the signal cancellation here because we're adding them. So if one of them ends up being like positive in a way that the other ends up being negative, you can end up with zeros where you don't want zeros. The parameters of three linear mappings are dynamically generated, which are decomposed into a dynamic input-dependent component and a static input-independent component. Given the input, it's first flattened and normalized. Then we follow the conventional HC to generate unconstrained raw parameters, A, B, and C, according to these formulas. After obtaining the unconstrained raw parameters, we then apply constraints described earlier to enhance the numerical stability. To be specific for the input-output mappings, we employ sigmoid function to ensure that they're non-negative and don't get very high, right? I wonder how they choose the 2 here. Why are we okay with C being twice as big as A? Is that obvious from the formula? Not obvious to me. Okay. As for the residual mapping B, we project it onto the manifold of doubly stochastic matrices M. This is achieved by, that's the sinkhorn that we saw, which first applies an exponential function B to ensure positivity, getting M equals exponent B, and then iteratively performs column and row normalization. This iteration converges to a constrained doubly stochastic matrix. We choose, okay, so 20 iterations to converge to that constrained doubly stochastic matrix. Okay, I'm still fuzzy on a lot of details. The thing that I'm going to guess, which I think is the answer to your question, how would someone even come up with this, is they basically observed that in the standard hyperconnection setup, this matrix B had high spectral norms. They probably observed that when they say they had numerical instability, I assume that that means that their gradient norms were getting larger than they should have been over time, or maybe even exploding. And they went to look at individual layers, and they saw a lot of spikes coming around what the HC was doing. And when they looked even closer, they would find that the spectral norms were just getting really big. And so they're like, what if we could just bound those somehow? Like bound the actual spectral norm of the parameters itself instead of just like, throwing more norms on the outputs. Because you can always throw more norms on outputs of different operations. But at some point, it starts to become really unsatisfying if the parameter itself is getting huge. And it's just going to be like, you're basically just, when you throw it, like when you take some large parameters, they're going to give some large outputs. And when you throw that into a norm, you're just doing like really weird information squishing at that point. So ideally, you keep your parameter better behaved as well. So I believe that's the point that they started at. For the rest of this stuff, it's really hard for me to say. I'm not, I had not heard of this original hyperconnection paper. Now I kind of want to do more, but I don't think I want this to be the stream where Matt just deep dives hyperconnections. That could be something for like a bonus stream. Something I feel like I need to do now. Because this seems like a good way to strengthen the residual connections between adjacent transformer blocks. And I really like the idea of having strong, well-behaved connections between my adjacent blocks when I'm thinking of diffusion models, because I'm thinking of how, like, to accelerate a diffusion model, a lot of what you can do is like cache the outputs of a layer, because you know that like the outputs of that given layer haven't changed much from the prior iteration, and you know that your information flows through that caching by the skip connection, right? And just so that it's clear what I'm talking about, because I know what I'm talking about so far has been pretty like crazy and complicated, so I will draw real quick. Okay. So I know we've been reading an LLM paper, but keep in mind, every time I'm reading these LLM papers, because I don't work on LLMs, I work on diffusion models, I'm always thinking of the diffusion perspective, right? And so what I'm thinking of in this case is, what's the best way to draw this? Like, when I have some block in my diffusion model, and I have some input, my input has to get processed by the block, but my input also goes around the block, right? In the form of the skip connection, because whatever I get out of this block, I have to add back to X, okay? What this means practically for diffusion models is if I have multiple steps, so I have X at, some noise level. Maybe this was at my step 49, so like my second step, and this was step 50, so it was like my first step. Sometimes what you end up observing is that you observe two things. you observe that in diffusion models, that the output of block B at step 49 is pretty close to the output of block B at step 50. And you also observe that this happens more for some layers than others, more at some steps than others. And so at steps where these outputs are really the same, you would just reuse this output here. You would just cache it and reuse it here and not do the inference here at all. But you can't literally like just load in here and keep going, right? You still use the skip connection. So that's how the information flows. You reuse the old B and you add it to the new X. And so the caching actually becomes this operation here. X sub 49 plus the prior output of B. And why this stronger residual connection thing sounds so interesting to me from the diffusion perspective is I'm not sure in which way it's stronger, but it should be one of two ways. Either this should be even more effective because it's not as dumb of an operation, or maybe my blocks will be less redundant with each other. And I won't need to do this, or I won't get to do this, but I'll get a better result. Although I am curious about one thing, and I want to go back to the code to see the one thing, which is, and this is important. Does it break diffusion caching completely because of how you compute the comp, the pre and the post? Would that completely break it? Where is that comp? Okay, let's see. For diffusion caching to work, I need to be able to do my plus equals. So I need to look here. Okay. So for diffusion caching to work, I would want to be able to take an old X, like an X from a previous step, and use the residual from the current step. I don't think I can do that because I need comb. And comb comes from the current step. I suppose I could use the old comb on the new residual. Maybe that works fine. In fact, maybe that's like a pre-step residual in a way, which is a little weird, but maybe that works. And then what could I do on this end? I need to do post times, no. This could be treated, this could be the thing I cache. I could cache this from the prior step. Could I always just compute that? I mean, this doesn't require any of the actual forward, right? I could just compute this with the current residual. So I guess I have options. I would kind of need to test those multiple options, but I have options if I want to do diffusion caching. It would still work. Well, it would still computationally. I could do the computations. I don't know which way I should do them. Like, I don't know if I should do the computation to get like a post and a comp for this step, and I only cache X, or if I cache the output of this and the comp. I'm not really sure. My gut says I compute a step-specific post comp, but I cache the last step's post. Because the post is so specific to whatever the last block was, but the comp needs to be a modifier on the current residual. But anyway, enough speculation. Hey Raj, no worries about being late. Can we share the links of papers we're currently reading in chat? Yeah, that's a good idea. Okay, now I'm going to do normal stuff. We did a little DeepSeek v4 pseudo deep dive. I don't think I explained their manifold constraint hyperconnection super well, except that it's from the perspective of trying to constrain the spectral norms of their mapping matrix to have the benefit of the strong residual connection without the issue of the param norms and the grad norms exploding and making your training unstable. So I guess we got that, and then we got, their compressed attention, which features some token level compression, some top case selection. We can either have a very lightweight step where we combine these two things and only have this branch, or we can have a heavier step where we do like a very quick indexing, but obviously it's not as quick as only doing the left branch. And I suppose while the dims are smaller, it does look like we're using more tokens than we use in the attention here, right? So maybe that makes it more expensive because we're still scaling, n squared, d squared. We're still keeping big N, so I don't know. But that's DeepSeek v4. For the next papers, I will share links so people can open them on their own if they want. Son, this has gotten so complex that you're more interested in the gaming than how the comp works. Fair enough. Yeah, gaming. What do I do for gaming? I play Slay the Spire. Not very well. Slay the Spire 1, I could do a 20, but like my win rate was bad enough to where like rotating, there wasn't even really a point. Um, Slay the Spire 2, I've only played a few times, and I only really play with friends. What else do I play? Uh, I play Sims sometimes, not the original Sim, but like simulator games. I like old ones that I grew up with, like you may not have heard of like Pharaoh or Zeus. If you were to have heard of anything from that line, it would have been Caesar probably. But like city building stuff is fun. Um, Sometimes I get in a mood and I end up playing a competitive game. Like I played Age of Empires 2 a bit, but like online, like laddering. Haven't played in a while, but I still watch. I play Minecraft. I play Minecraft with my kids. I tried to get into Minecraft speedrunning. I'm just so bad though that I kind of didn't. But I like watching Minecraft speedrunning. Is there anything else that I play? I used to play League of Legends. Sometimes I'll randomly get really into Teamfight Tactics, and I'll play that a lot for like a month and try to rank as high as I can. Um, but yeah, not a lot of gaming lately. Mostly just a lot of working. Can open my Steam and look at the hours. I've edited something really low that would almost make me feel weird about how much I work and how little I play. But whatever. Um, okay, have you checked out text diffusion models? Good stuff happening in that area recently. Yeah, I've kept like the vaguest of tabs on it. We are going to see one today though. Um, this one. We're going to see one in a minute. So, have I kept an eye? Not the closest of eyes, but we'll go through one and we'll see what it's looking like. I guess I remain skeptical that that's a great way to generate language, but I do think it's better for generating images and videos than autoregressive, so maybe it's better for text. Like, why would text be that different? Well, I guess the reason text would be that different is because text wants to be and is discrete, whereas image and video wants to be continuous. And so my little intuition would just be like autoregressive is a better way to operate on discrete, and diffusion would be a better way to operate on continuous, or it's more like diffusion's just really overkill. If we've got these nice discrete like things that we can separate really easily from each other. But I don't know. We'll look at that paper. Maybe they're going to prove everything that I think totally wrong, and diffusion LLM is totally the way to go for LLM. I don't know. Anyway, let's look at this one first. Let's get a timer going. This is the first time we've opened up the timer. But in my defense, I don't know. I think that deep dive was kind of cool, even if I am missing personally some of the context to give like amazing insights. I think it's fun to just try to figure it out. And hopefully if we do that every time, like eventually I'm just a little less dumb and I can get a little bit more of it like really, really quickly. I'm not an LLM guy, but I can become an LLM guy. Some stuff just needs to be sequential, so this is a limitation of text diffusion like web search, tool calling, etc. Yeah, but some stuff sort of needs, like the fact that some stuff needs to be sequential doesn't mean like, okay, I don't think anybody, once again, not looking at the paper in front of me, I don't think anybody is saying we can do fully bidirectional diffusion for like an entire text task, right? You're always doing chunks. There's a question of like how to handle history among your chunks, if that should be AR or if that should be something else. But you're always doing chunks. So I don't know if that's a weakness, right? Because it's not like your tool call was ever going to fit in your bidirectional diffusion context anyway. And to be fair, I don't even know how much they're doing bidirectional. I assume they're doing bidirectional attention because that's how diffusion works, but maybe they're not somehow and I'm just dumb. We'll look at their paper and maybe they'll teach me. Okay, let's look at this paper. I'm going to take a sip of water, take a deep breath, check the chat, and then we'll read a Schmidhuber paper. Okay. Last week was crazy. Oh yeah, we got GPT 5.5 as well. I guess I don't think about that one as much because there's basically never details. So I guess it's nice when my stuff gets, when my code agent starts working better. But other than that, it's not like it's that exciting from the research perspective. Okay, I think I'm caught up. I think I said hi to everybody. I said hi to Hassan. Had said hi to Ziris. Said hi to Raj. Yeah, I think we're good to go. Okay. All right, neural computers unify computation, memory, and I/O of traditional computers in a learned runtime state. They want a completely neural computer, so a mature general-purpose realization of the emerging machine form with stable execution, explicit reprogramming, and durable capability reuse. Neural computer primitives can be learned solely from collected I/O traces without instrumented program state. We instantiate neural computers as video models that roll out screen frames. Okay, so we're generating frames from instructions, pixels, and user actions in CLI and GUI settings. We show that they're going to acquire elementary interface primitives, especially I/O alignment and short horizon control, while routine reuse, controlled updates, and symbolic stability remain challenging. Okay, so it's like we're going to show someone desktops that look really plausible in brief moments, but they're not going to stay consistent with each other, right? But yeah, it's basically text to like computer screen or pixel to computer screen. That's interesting. Um, what's like the method here though? Is it okay? Dang, timer done. What is the research problem? Pretend to be a computer with a video model. Sorry, what's the research problem? Computers? What's the solution? Pretend to be a computer using a video model. Does it work? No. Okay, this was my warm up. If I focused, I had my questions answered within 1 minute because they answer it all in the abstract, right? That's not, I don't like to just sit in the abstract. This one just, I was so surprised by the task. I was sort of stun locked in the abstract that whole time. I love this. Classical computer, compute, memory, I/O. It makes it seem like so simple, right? Neural computer, latent runtime, neural compute, neural memory, neural interfaces. We did have an architecture down here. Let's take a look at that. It was like here. Okay. Terminal frames are observations except t. That makes sense. That's like our image input or our image frame output. A prompt and the first frame seed the conditioning stream. Do we always need a first frame? Where do we get the first frame from if we actually have like a fully neural computer? Oh, and it's WAN 2.1. WAN 2.1 based latent state Z sub t rolls forward under the standard ITP sampling scheme. How do we get I? That doesn't make sense. It's just WAN though, right? This is literally just WAN, except the output is our computer screen. So this is almost like one of those papers that a lot of time you criticize a lot, where it's like, oh, take some existing model and just like fabricate some random application for it that it does like in a really half-baked way. But yeah, I don't. To me, this seems like I would always just want my computer to be a computer. I don't see why I would ever want it to be an AI model. Um, and I don't think there's anything really technical novelty here, right? It's just we mine data, some diverse open-ended terminal traces, or some Docker scripts with cleaner, better pace buffer. Yeah, we just get screen data basically. We get screen data, we get conditions connected to screen data, we fine-tune WAN 2.1. Okay. These are good side projects for research teams. I don't know. I'd be pretty bothered if my research team was wasting time on something like this, but that's just me. Good for them. It's cute. I think I would feel a lot better if like, I don't know. I don't know. I'm gonna try not to say too many mean things on the stream. Let's just go to another paper. It is cool for us that we get to see how something like that would or could work, even if it's not like inherently a very useful thing. And I do like, okay, I it's hard because part of what I think makes research so fun is just like the raw curiosity and the can this work of it all. So I should be careful. It's like I don't think there's anything wrong with doing stuff just because it's cool. Maybe I'm jealous that they get to do something just because it's cool. That's what it is. I'm just jealous. Time to buy a neural computer for 2000K USD. Yeah, sounds about right. $2 million. You could get yourself a like a no 2K. You might be overshooting with 2 million. Let's see. How much for H100 node? No, I want to buy it. I want to buy one. It's just $300 to $400,000, and then I don't know if it comes with all the crap you would need to set up with to keep it cool though, because each one wants to run at like 700 watts. So wait, could your home outlet. Does the power grid give you enough power for that? It does, right? Yeah. But yeah, you'd probably have some other like setup costs. You have to install some kind of cooling thing. Maybe like re-divert a local river or like you could dig down into like where the storm sewer is and you could like siphon water off of like the public storm water, right? You could use that to cool it. Um and yeah, then you have your own PC that according to them can't really stay consistent for more than a few frames. I should be careful. Maybe that's a part that's kind of solvable, right? And eventually it gets more consistent. And it is all just pixels. Hypothetically, if you're getting none of them, the model should be able to learn how to be consistent, right? I don't know. That's kind of a, yeah. Time to buy a $2 million computer that's kind of just weighing underneath. There are special lines for power that becomes commercial, except it can't become commercial, Raj, because it needs to be my personal computer. The whole point is I want to own this. I don't want to pay to have it be like in the cloud, you know? I want to like paint it. I want it to look like One Piece. It can be down in the storm sewer with like my One Piece splash art on the side of my H100 rack, right? So I guess like the rats that wander by can enjoy my One Piece H100 server, which puts random pixels on my screen. I was actually thinking about this because I didn't see this paper. Whoever, Hassan, did you suggest it? I didn't see the paper, but I did somehow see the discussion. And so I was just thinking the other day, like, how would I stream on a computer which is just doing random stuff all the time? Or like showing me pixels? Like, what does that even mean? Would I hook the WAN up to like a clawbot and the clawbot chooses to send the WAN pixels over the internet to, you know what I mean? Like I guess it's not a personal computer, right? It's just a GUI simulator. So I would need like I would need an actual computer to take my random GUI and send it to you. And then do I need to expose the internet to my WAN so it can like simulate the pixels corresponding to this paper? It'll like retrieve the document and then like hallucinate it for me? I don't know. Maybe I'm being too mean. Let's look at another paper. Someone said, have you kept track of diffusion LLMs? The answer is not as much as I wish I did, and I'm about to pay for it dearly. Unifying multimodal understanding and generation with diffusion large language model. Okay, so we're going to be interleaving text and image somehow. I almost want to just skip to a diagram because, yeah, details aren't jumping out at me, except this is some MOE-based DLLM backbone and some diffusion decoder. Let's take a look at the architecture. Okay, so we have a text tokenizer and a vector quantized siglip that's going to give us discrete text tokens and discrete siglip semantic tokens. We're going to have separate text and text detokenizer and diffusion decoder, where we're going to decode the discrete diffusion tokens. So I guess this is like a discrete diffusion refiner head, right? Wait a minute. It says it's a diffusion LLM, but okay, this is how little track I've kept of diffusion LLMs. Sorry, I paused and got really confused because I get here and then I'm like, what even is a diffusion LLM? Like, this is looking in, like, I guess I thought that the diffusion LLM was itself denoising tokens. And so I'm confused to find a diffusion decoder sitting on top of it, but only for images. That's what stun locked me. Um, which I guess reveals this might be the first diffusion LLM paper I've ever opened up in my entire life. Anybody want to tell me real quick how diffusion LLMs work? Or is there some paper here? Let's just go to the original paper, so that I never make this mistake ever again until I die. Where is it? Where's the first diffusion LLM? LLMs. Blah, blah, blah. Unified modeling. Okay. Sorry, guys. I'm just looking for the first diffusion LLM. Is this one, right? We're going to get to this paper. It's going to turn out I've read it, and then oh, it's from Stefano. Okay, because I know that Stefano has a diffusion LLM startup, actually. So I guess it makes sense that he was like the OG. All right. No diagrams, though. Oh, you're killing me. Diffusion models have fallen short on discrete data domains, such as natural language. Crucially, standard diffusion models rely on the well-established theory of score matching, but efforts to generalize that discrete structures have not yet yielded gains. We bridged the gap by proposing score entropy, which is a loss that extends score matching to discrete spaces. So there's score entropy diffusion model and standard language modeling tasks. For comparable model sizes, it beats existing language paradigms by reducing the complexity. Oh, it beats the existing language diffusion paradigms and is competitive with autoregressive models like GPT-2. And it generates faithful text without requiring distribution annealing techniques like temperature scaling, and can trade compute and quality. Similar quality with 32 fewer forward passes. Okay. But how is the actual, like, okay. Does my model, like, I do diffusion with the model itself, right? Like, I will generate sequences of a certain chunk, and I'll, like, iteratively denoise them, and then I'll finally use the text decoder at the end? I'm not confused about that, right? Is the only thing that threw me off with that multimodal model the fact that they're getting, like, final text tokens that they still need a diffusion model to translate back to image space, I guess? Is that the issue? Is that the only thing throwing me off? Do they talk about the sampler here at all? Do they talk about the sampler in the paper that we're in? SigLabVQ tokenizer to convert images into discrete semantic tokens. A big, well, not very big actually, pretty small diffusion language model that processes both text and visual tokens under a unified mask objective. Sorry, I zoomed at the wrong moment. Okay, and then a diffusion decoder that reconstructs semantic tokens into high fidelity images. I think it's the thing that I said. I think the point of the diffusion decoder is just you get good tokens, but they're not image tokens, and so or they're not like ready to decode image tokens, and so that's the job of the diffusion decoder. Semantic VQ requires a specialized decoder to map features from the semantic space back to the image space. Okay, that's what it is. Unlike traditional reconstruction-based VQ that can directly use a pixel. This is the part that confused me. I feel less bad now about myself. I was expecting to see this, and instead I saw this, which made me question the diffusion of it all in the first place. But it's just doing diffusion 2 times. And they use the Z-image base, which is a 6B model, and once the diffusion LLM generates image tokens, they serve as the conditioning signal, replacing conventional text prompts. Oh, so the final image tokens, which are kind of coming out of our text model, sort of text. Okay, so it's almost like this model's job is to generate text token input for the diffusion decoder. That's the way I'd prefer to think about it. If they're saying they're just using it as conditions for the Z-image base instead of the text, that's how I'm going to choose to see it. So it's almost like it's not a multimodal model. It's a model that generates some text and then generates some like latent space diffusion prompt. Right? Am I crazy? I think that's actually what they're doing. 50, okay, we employ model distillation on the Z-image base to achieve 8-step CFG-free inference. Yeah, I mean, the fact that they would need 50-step in the first place just means we're generating this image from scratch, right? It's like the unified diffusion LLM didn't do anything for us except give us a latent space prompt, which actually just means we have to do a ton of work to like make it feed into the Z-image base nicely. It almost makes me think we may have been better off just like having it write this in text. But I guess the advantage that this gives us is we needed to ingest. No, we don't need to. I mean, this is when we want to ingest images. When I want to generate an image, I might only be giving text, which this basically takes my prompt and turns it into a different prompt. That feels really silly in terms of not that this is not a paper that's moving the field forward in some way, but it feels like a very silly way to try to accomplish the task of generating the images from text. I wonder, what I'm always looking for with these papers is if they've like constructed a compelling narrative around the interleaving, where that compelling narrative around the interleaving ideally would look like 2 things. The first thing I want to see from a paper that's doing this interleaved unified modeling image text is that doing this outperforms doing either of them separately. I guess that's the holy grail of it all, is like using image and text together should improve both image and text. And most of them fall short in this way. The second thing is I'd really like there to be tasks where I need to generate both image and text, and like a good benchmark that convinces me, yes, I wanted to generate the image and the text together. Because what I typically get instead in papers like this is I'll come to the tables and we'll be doing just either reasoning tasks, like, sorry, general tasks, which are like some kind of question answering tasks or some kind of detection tasks, or reasoning tasks, right, which are text tasks. Are these actually all text tasks? These are all like text plus image to text tasks, right? That's why the Changlin 2.5 can even do them. So far, we're in table 2, and table 1 I think was just like some setup, right? If we find it. Yeah, table 1 is just describing the training stages. Yeah, just 3 training stages. What are the resolutions? How much data? It's not a lot of data. It's not very much data. Anyway, so far, only text outputs, okay? No image outputs. Our image outputs are going to be on an image-only benchmark, right? Or like the only outputs are images. Why is it GeniVal? What year is this paper from? Like you put this on throw me like at least have GeniVal 2 somewhere, I hope. Like we don't need to be on old crusty saturated benchmarks when there's newer ones. Is it really just GeniVal and DPG? That's annoying. But anyway, there's still what I'm saying, image outputs, right? So we have our text output paper and our image output paper. What I'm still waiting to see from the image output paper, image output benchmark, image output benchmark, image output benchmark. This is the only thing that comes close to it for me, is where like you'll need to generate something that'll have world knowledge that like maybe your diffusion model doesn't have, so it'll require some lookup. Like we saw this in a paper a couple weeks ago. This is like, okay, you know, obviously we're just evaluating the image itself, not any of the text output, but like we at least get to use the thinking capability, right? Because this requires some like reasoning or world knowledge. So this is better than nothing. But still, it would be really nice to see some, yeah, this is more image editing, and this is multi-reference image, yeah, lots of editing. So like they're saying, since it's a language model, it can do things like reasoning, it can even do like maybe tool calls or things like lookup. But I mean, we can get image and text out of this model at the same time. Is there no task where that should be useful? Maybe that's what we're getting to here. Intergen bench. Maybe I've been whining the whole time. I've actually just been, it's an alley-oop. My whining sets them up to deliver the thing I've been looking for months. Let's see. So, a skateboarder launching off a concrete planter, gliding, blah, 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 blah. A skateboarder in a black hoodie and dark pants is captured in midair launching off. Sorry. Okay, so I give them a prompt for a story, and then it's going to tell the story with images and text. That's cool. Event forecasting. I will give it like a question about something that happens in the future, and it will answer me and show me. Okay. Cooking process for cooking the wings. It'll give me like an integrated recipe video, like a recipe blog where it shows me the examples of what the process should look like. That's cool. Okay. I like it. I like it. And yeah, I mean, it's their new benchmark, so they don't rerun it. I guess they had access to this code or whatever, so they could run this, or maybe there's some API exposed. Okay. The numbers, I don't know if I need to see how the numbers are computed for the scores. It looks like it's just LLM as a judge, right? But is it just asking the judge to rate it like from 1 to 10 or something? Here's a case, like I said, some of the papers have been doing this, and I think this is fine. It's definitely better than nothing, where it's thinking in images a little bit, right? Like this is good. Give it a chessboard, ask it to do a thing that requires it to think about a few moves. Granted, with text, with chess, there's so much chess in chess books written in algebra. There's texts that are only written in like chess algebra that this is probably counterproductive even. Honestly, this isn't too compelling either. Like, you can solve this just with math formulas. I doubt that either of these things are very helpful, but the general idea of like visually planning for things could be helpful. They just happen to pick two cases where the planning should happen with chess notation or the planning should just happen in like text and math. Like, the diagram might help me, but I don't see any reason it should help the LLM at all. Okay, sorry, I wanted to get one more detail from this paper, which is constructing their benchmark, getting the scores. Do they just ask the LLM to evaluate it like 1 to 10 or 0 to 10? That shouldn't be so hard for me to find. Maybe I'm just dumb. Okay. Utilize advanced VLMs to assess performance across 3 dimensions, text coherence, text image alignment, and ID consistency, but I don't see those broken out here, right? So it's like we've averaged them. If it doesn't tell me anything else, I'm going to assume that they basically asked it to score the text coherence, the text image alignment, and the ID consistency from 0 to 10, and then averaged. That's what I think I'm seeing. Okay. We spent more than long enough on that paper. And sorry, I'm not looking at the chat enough when I'm doing that. I get in this mindset. Okay, I'm about to read your messages. I'm sorry, everybody. I get in this mindset where I'm about to finish the paper and I just kind of want to like go until it's done, right? But I know that's like, that I ignore you guys. I'm sorry. Okay, Arena. Hey, Matt, I have a question. What do you think about time series / forecasting domain? What are the career prospects that you're aware of? I think that is generally a lot of what like ML and finance is, right? Is trying to predict like short-term or medium-term futures in stock. So I guess a lot of finance, but it could be a lot of everything, right? It's actually, you picked the perfect time, Arena, to ask this question, because what the heck is that startup called? It has a weird name, like Comfort, but the name's not Comfort. Can someone help me? Um, Help me out here. It's a new startup. Oh God, I ignored the chat for 20 minutes. That's horrible. Um, what's this startup called? It's got a really weird name, but they're just trying to like predict future events. Ah, I feel like an idiot putting this in Google. Um, there's a brand new one. Nope, nope, nope. What's it called? No, I need more. Should I go into ChatGPT and ask it to do a search? Is this it? No, not human intelligence. What is it called? I would really like to find it because I feel like what they're doing is a very specific answer to your question, Arena. Now I'm getting desperate. No, like, dang it. I know I'm saying something vague, but the thing isn't vague at all, and I saw it this week. Oh my God. I would say they raised like $800 million, but I don't think that really distinguishes them from anyone else these days. Dang it. Oh, it's like on the tip of my tongue too, and I just cannot for the life of me remember it. But anyway, okay. I wish I had proof, but I did see a big raise recently, Arena, for a startup that specifically proposes to try to predict like geopolitical events. Um, so I think like traditionally maybe time series forecasting is a very constrained problem. I think lately there's a big interest in moving beyond the typical constraints and just doing very poorly constrained time series forecasting, where you take, even like large historical events that are separated by very irregular time intervals and trying to predict and model the probability of different events happening in the future based on that. I'll also raise a bunch of $1 million for my new startup for creating neural computers. Yeah, raise $5 million and you can afford 10 neural computers. It's a great idea. is just like BERT, slow as hell since you can't KV cache like usual. Sorry, what was I looking at when we talked about, were we talking about diffusion LLMs when you said that, Sams? You can't KV cache like usual, so the diffusion LLM ends up being slow? Or did you mean something else? Because I think you can still do some KV caching, right? Because like across chunks, you have some cache. I don't know though. I don't know enough. I should be careful what I say if we're talking about diffusion LLMs. Feel free to clarify that, Sams. I'm so sorry. I need to look at the chat constantly. I'm still learning to be a streamer. Mercury is the startup by Stefano? Okay. Yes, very similar to how images work. Do they compare with multimodal autoregressive LLMs? Oh, sorry, Raj. Did I give you the comparisons well? Let's see what they did compare to, actually. I think you probably saw it because we went through the tables, and so hopefully that answered your question. Oh, you asked if they compared to autoregressive LLMs, not necessarily like they compared to these VLMs, right? Bagel's autoregressive, isn't it? I think most of these are. I don't think any of these are. I suppose this one's diffusion. I think this one's diffusion, and I think these are both AR. On the general tasks, Bagel beats, loses. So Bagel wins 6 out of 7 on general. On reasoning, Bagel wins 1, 2, 3, 4 out of 5. It loses math vision. Okay. For OCR, Bagel loses, beats, loses. Okay. 1 out of 5. So it's decent on this OCR and chart, which probably comes down to the data, right? Because even like Lotta O was better than Bagel on that. It's probably a data thing. Other tasks, counting. Bagel loses. Okay, so Bagel is better on the general and the reasoning tasks. Lotta is better on the OCR and the other tasks. I don't know if I would consider Bagel 1 year later to be anything resembling Soda though, but I guess it's what was available to them at the time that they were running this. Okay, next paper. Did I get questions done? So sorry again for being bad with chat. That's something I just got to learn and get better. Okay, let's hit this paper. So 1VL, one-step latent reasoning and planning with vision language explanation. So I was curious about the one-step. I was also curious what they meant by latent reasoning, like if they're doing a reasoning pass without ever decoding to text or something. First, latent chain of thought method to, okay. I think latent chain of thought is already a thing, right? People have already been doing the reasoning in the latent space without decoding back to text space. But it's the first one to surpass explicit chain of thought, they say. Okay. So the research problem is speeding up the chain of thought by doing it like one step and by doing it implicitly in the latent vector space because it's fast, right? Explicit chain of thought is interpretable, but implicit chain of thought is fast. And they're saying they beat the explicit chain of thought. So they're telling us that it works, right? But what is their solution, right? Because people have tried the like implicit chain of thought before. They're saying that the problem is interpretability. They're not saying that they're interpretable. They're saying that it's more accurate. And their solution is, instead of opaque latent vectors, they get future frames, or they get, what? I don't understand. What is different here? So yeah, vision and language, fine. And then they use some prefill and then it's more accurate. But I wonder if what's happening here is that I'm not understanding, or maybe their motivation is kind of hand wavy. But it looks like we're going to take our vision tokens and try to predict future frames. And we're going to take our language tokens and get chain of thought text. But the result of doing that gives us tokens that we can do some implicit chain of thought on. But if we decoded them at any time, we could get the text or we could get some future frame, and that's how it's interpretable. I don't know, but they're not pitching interpretability here. I'm still confused. Okay. 2 types of latent tokens, vision and language during training. Oh, during training, dual auxiliary decoders decode these into future frame visual tokens and chain of thought text, respectively, which provides rich text and world model supervision. During inference, the decoders are discarded and the latent tokens are pre-filled into the prompt context, matching the speed of answer-only prediction while keeping the interpretability of A. Okay, so they are saying it's interpretable. Because I could decode the latents to future frames, I could decode the latents to text. It is interpretable. But they pre-fill them into the prompt context during inference, matching the speed of the answer-only prediction. How does that match the speed of the answer-only prediction? We still need to compute the tokens. Like, we don't need to decode them, but we do need to compute them in the first place. But I guess our vision tokens don't have anything to... What? Hold on. Is there another diagram here? An image and structured text prompt are fed into the VLM. The output hidden states shown below the VLM contains image tokens, text tokens, visual latent tokens, language latent tokens, and trajectory answer tokens. During training, hidden states at the latent positions are routed to 2 auxiliary decoders, which directly predict the future frame visual tokens, and the language predict the chain of thought reasoning. During inference, both decoders are discarded. Latent tokens are pre-filled into the prompt, matching the answer only. Oh. Wait, what? No, I'm still confused. Oh, I guess these aren't AR because I have some learnable like vision and like language latent tokens, and as I pass those through, I can just sort of trust them, and they are implicitly my chain of thought because I've regularized them during the training to where I can get future frames out of this one, and I can get some chain of thought text out of this one. Okay. I guess that's what's happening, right? We're never auto-regressively predicting these. We always pre-fill them. They must be learnable if I actually look at them, right? Yeah, so they're placed in the assistant response before the trajectory answer, and they occupy the positioning where typically the chain of thought reasoning would appear, and the hidden streaks extracted at these. Okay, so they're still not... I assume the latent tokens are learnable. So 2 language latent tokens, 4 visual latent tokens. Reasoning carriers whose hidden states at the VLM output layer fed into auxiliary decoders. During implementation, we found that dedicated special tokens to the VLM vocabulary causes performance degradation, so instead they represent latent tokens using the original vocabulary. What? Wait, okay, now I'm confused. So we have a sequence of 4 visual latent tokens and 2 language latent tokens, but the vision latent token is realized as 35 tokens, and the language latent tokens are realized as 20 tokens. Am I crazy? What am I missing here? I have 2 visual latent tokens that are realized as 35 tokens. I have 2 language latent tokens that are realized as 20 tokens. This is probably obvious. It is not computing for me at all. I'm not sure what you're talking about, Raj, with the Oh, you're suggesting more startups maybe that are the ones I was talking about? Sorry, I didn't notice your message before because it was doing weird translate bug stuff in the chat. Those are not the ones I was thinking of, no. It's okay. I'll probably see it next week or during this next week, and then I can just mention it once I remember. Anyway, anybody understand this? Because I'm not. I want these to just be some random learnable tokens, but it sounds like they're not. Instead, there's something else that is just not making sense to me as written. We use the original vocabulary. Okay, but what things in the original vocabulary? That's what I'm not understanding. Maybe they'll say, like here. No, they're really not. At inference time, the auxiliary decoders are discarded. The latent tokens, both visual and language, can be pre-filled as fixed token sequences because their specific vocabulary identities have been seen by the model during training. So the inference property is constructed as start latent viz, end latent viz, some latent viz. All latent tokens are included in the prefill phase rather than the decode phase, since modern transformers process the entire prefill in parallel. These additional tokens are basically an overhead, especially if we're only using 2 or 4 of them, right? This yields inference latency almost identical to answer only AR predictions, and allows us to do all these tasks. I'm still not whatever. That's a detail that I guess is stuck in code. So they have 3 stages though. The fundamental prerequisite for our auxiliary decoders is that the main model's latent tokens carry information that's semantically aligned with the reasoning content. Yes, the latents have to have the content. Without targeted warm-up, these tokens do not produce meaningful hidden states that auxiliary decoders can decode. So what is stage 0? So train the main VLM end-to-end on the trajectory prediction task. With latent tokens embedded in each training sample's assistant response, the model learns to predict accurate trajectories because that's the task, and we're doing end-to-end, and we have the CE loss over the trajectory answer tokens. Oh, but we do also have the CE loss on the latent tokens. And we develop the meaningful latent representations by contextualizing the latent tokens within the prompt response to structure alongside the trajectory targets and computing loss on both. The model learns to use the latent positions to encode intermediate representations useful for trajectory prediction. That all makes sense. I guess what I don't understand then is what the heck stage 1 would be. With the main model producing stable and meaningful latent representations, stage 1 focuses exclusively on training the auxiliary decoders to align with these representations. So they freeze the main model so that the auxiliary decoders optimize against a consistent semantic distribution. So in this stage, we just trained the auxiliary decoders. Okay, so wait, what? Then what's the loss here? Okay, sorry, I missed this. CE loss over the latent tokens. How am I doing a CE loss over the latent tokens if I don't have the decoders? Oh, just ARCE loss. Like autoregressive loss. This is autoregressive. And we've put the latent tokens towards the later positions. So my latent tokens are trying to predict next latent token, and my last latent token is trying to predict trajectory answer token, and my trajectory answer token is everything in context. I guess that's all that's happening here. Now I train the decoders, and now that I have the decoders, I can introduce my fancy losses with the actual decoders to regularize the latent representation space while training the model end-to-end to accommodate that, right? Yeah, fine-tunes all 3 model components. Okay. A virtuous cycle. Ooh, that sounds nice. I should put that in my vocabulary. Instead of a vicious cycle, we can have virtuous cycles. Richer latents enable the main model to make better trajectory predictions, and the auxiliary decoders adapt to the updated latent representations, which improves the explanation. Now, the big question is, how well does this work, right? The motivation sounds nice, I guess. We wanted low latency, which we get latency basically the same as the answer only, which is what we're going for, right? We want to have the latency like the answer only while having the benefit of the chain of thought. And on this specific benchmark, which I think is some trajectory prediction benchmark, they get the better score. Better latency, better score. Basically the same as, but maybe a little bit better than AR chain of thought plus answer. And the vision is interpretable as well, not just the language, right? Because we can decode those latent language tokens to be some chain of thought. We can also decode the vision tokens to be the future frames. And since these are all like trajectory prediction tasks, we care about predicting future frames. So this is like a very meaningful way to do that. Yeah, I would say this seems like it works. It's faster. The performance seems to match the chain of thought for the methods they choose to compare. The one way I could be getting bamboozled is this comparison could be total garbage. Like, these are not models that I know of off the top of my head. But obviously I'm not going to know about them because I'm not very familiar with these trajectory prediction benchmarks. So are these the right models to compare to? I don't know. But the numbers I am seeing look good. So I like that. Okay, let's keep moving. An agent specification execution language. So language model agent systems rely on reactive prompting in which a single instruction guides the model through an open-ended sequence of reasoning and tool use steps. So yeah, the agent just has to figure out how to orchestrate, right? So there's lots of orchestration frameworks that try to put structure but they tightly couple the workflow logic with Python, which they say makes the agents difficult to maintain and modify. So they define a language for specifying the LLM agent workflows that give explicit control flow modular structure, and I guess basically decouple that with Python, right? And a customizable agent harness. So it supports type steps, branching, and loops. So is this like basically a programming language paper, but like specifically for the LLM agents? Agent definition, agent harness, an example of the agent specs workflow for topic research and summarization. Okay, so it's like YAML files. It's like special YAML files specifically for agentic frameworks, I guess. And then under the hood, like, is the agent consuming these mainly as text? YAML syntax for specifying agent workflows with explicit control flow and modular structure. Agent spec supports type steps, branching, and loops. Blah blah blah. Agent specs is the executable specification which agent workflows are expressed in declarative, human-readable YAML files. Skills and agents are both represented as workflows and can be freely composed, giving users direct control. And I guess the LLM, or like, the underlying model would just consume these YAML files as text. Or did they do some conversion step for you? They give you a visual editor that generates the YAML specifications for you. Our LLM is just reading the YAML though, right? I don't see any reason to believe that's not what's happening. But that's cool. Easy to get through pretty quickly too. Extending one-step image generation from class labels to text. Oh yeah, I wanted to see this one. I wanted to see what GPU providers do you use for personal projects. I spend all my time working on work projects, so I don't have personal projects. Maybe other people in the chat have personal projects that could answer that question, Raj. I just use whatever we use at work, which lately it's AWS where I am now. Extending one-step image generation from class labels to text via discriminative text representation. Our model achieves superior image quality instruction following, blah, blah, blah. Okay, where's the one step though? That's all I care about here. How are we doing one step? Nope, doesn't tell me. Cocoa train set, what? Okay, I saw retrieval. I wish I was seeing like a method diagram, but it's okay. Let's go to the method. To avoid costly OD integration, standard flow matching inference, meanflow learns a flow map that directly predicts a transition at some time step. Okay, different text representations show distinct few step generation potentials. Existing studies on meanflow have achieved significant progress in class label condition image generation tasks. They want to extend meanflow to T2I. Reducing the number of generation steps limits the model's refinement capacity from the perspective of velocity field. Blah, blah, blah. Blip 3.0 next. Maintains okay. The results in figure 2 for the... What? It's just meanflow? Is that all we're doing here? I'll just zoom in now. I'm not going to spend any more time on this paper if the one step is just garbage. Yeah, this is not okay. Like, this is not mind-blowing four-step inference. This is four-step inference will give you some things with like limited detail that you can cherry pick, right? Where the textures are just extra fake. And there's a lot of like little inconsistencies, right? This is what I expect to see from four-step without, thinking, oh, you have some new method. And then the one-step is just terrible, right? Even the four-step here is bad. Why is the four-step here so bad? And sometimes, by the way, it's not clear how bad it is until you see it next to, anything reasonable. Yeah, I'm not... We encode query prompts using different text encoders, retrieve the top two similar texts, and visualize the corresponding... So, okay, they are saying they have like a better text encoder somehow, but I don't know if I find that very compelling because I already have my own opinion about text encoder for diffusion, which is that you should just be using an LLM as the text encoder. And that'll give you like optimal granular controllability and instruction following. Do they have like a diagram for this text encoder? Because that's what they're pitching, right? They do say, I didn't pay enough attention to it, but they do say via discriminative text representation. So they're saying they get like a, okay, we find that integrating powerful LLM-based text encoders using conventional training strategies results in unsatisfactory performance. To uncover the underlying cause, we conduct analyses and reveal that due to the extremely limited number of refinement steps in Meanflow, such as only one step, the text feature representations are required to possess sufficiently high discriminability. Okay, so they are saying they know that the LLMs are important, but the LLMs they say specifically degrade in this low step regime. And guided by these insights, they leverage a powerful LLM-based text encoder validated to possess their. Oh, okay. So they don't. Okay. So these guys are using the Blip30 Next because they say it's already got a discriminative text representation, which they say is going to give us better low step generation. Even if overall, I kind of like these better, like these. I like a lot of the way that they did the textures better, but I suppose, like, obviously these are better, right? Okay, I think this is important to keep in mind when you're trying to do the low step diffusion. Except, okay, here's the only thing. My belief is there's no reason to ever go fewer than 8 steps because it's always just bad. So don't do it. And in that case, it doesn't really matter which one we use. This duck looks fine. They do say there is still a gap in the gen eval between those two, and I guess the vanishing point is 12. I would not use either of these personally, right? I would use like a Quen or something, and I wonder if there's even a gap at all. I mean, even at 12 steps, that is vanishing. So I don't know. Important thing to keep in mind, I guess, going towards low steps with like modern text LLMs as your diffusion text encoder is maybe you want to be careful when you're trying to distill your diffusion model down to low steps because you could be shooting yourself in the foot with whatever you're doing with the text encoder. There's lots of ways to shoot yourself in the foot though using LLMs as text encoders. One way is just like you need to make sure that you use a chat template that is long enough so that your encoded text isn't garbage, but like short enough that it doesn't start to dominate your training time, right? Hey Ifta, how's it going? People are trying anything nowadays. Yeah, Raj, people are trying anything nowadays. Yeah, hi Ifta. Okay, more papers. Let's pull up the timer. Robust and realistic virtual try-on for diverse fashion items. I mainly want to see the method here. It looks like based on their radio plot that they say they're going to beat all the proprietary stuff, right? They'll beat Nano Banana, they'll beat Seedream, they'll beat GPT Image. I wonder how much they're going to share then, if they're better than these proprietary things about their method, versus how much is this just a high-level tech report. But their training and inference pipeline is rewrite the prompt and pass that to a text encoder, and then pass that to a unified multimodal image editing DIT, and then get an output image. Pre-training for general editing, progressive resolution continuous training, high quality vertical domain, data, supervised fine-tuning, reinforcement learning. Okay. So first we have our general editing model. Then we want to make it do higher and higher resolution. Then we want it to be trained on domain data, SFT, then RL. Then we distill it so that it's fast enough to be used in production. That seems like a sensible pipeline. That covers the solution I think they're pitching to us, right? We'll see if they're going to give us more technical details, but I don't think so. So in other words, I did my speed run. We saw it doesn't work up top. We have the radio plot. They say they do better than the Seedream and stuff. The one thing that I want to see, okay, in academic grade virtual try-on, and I only know academic grade virtual try-on because I just reviewed one, I feel like they often feel like hybrid images and not like clothing try-on. And so I'm actually curious to spend a minute to go through some of these examples and see, does it feel like it just does hybrid image with the clothing, or does it really feel like it does a fair try-on? And especially where I felt like it was hybrid image is often what I was seeing in the papers is it would like rely on the original image to give it like pose details that I felt like it shouldn't have gotten from that model. So that's what I'm really curious to see here is like, okay, no, this is pretty cool. Um, this is fun. I like industry grade Tryon. Academic Tryon felt really stupid. This seems pretty effective, and the pipeline is very common sense, right? Editing model, make sure it can do high res, SFT on your data, RL also on your data, and then distill for the fine tune. Um, do we get any comparisons against their competitors? I'm really curious. Is that from Ninja? Hold on. Sorry. I scrolled right past I'm trying to remember the character's name. I should show that to my wife. She would think it's pretty funny. Um or I bet my kids would get a kick out of it. I'll save that for later. Grab that real quick. Because the thing that you're really looking for with Tryon is that it's like you need to be careful that like especially if your clothes come from some model like source image, you don't want that to like mess with how your character looks. And that actually is immediately one thing that I'll criticize about this one is I feel like it erased his gut in a way where if anything putting a belt on him right here would just make his gut like even more noticeable down here. And instead we're actually kind of borrowing her figure, right? It's like suddenly he like it's treating this like his waist, basically, and he doesn't have a waist, or he does, and it's here, and it's bonkers, right? So this is funny, but if anything, this to me is like a failure mode, right? Um, yeah, I'm not going to spend too much longer here because there's so many pixels that it's like slowing my browser down, and we can barely see it. Uh, I think there are Tryon based on Gaussian splatting as well. They're the best. Really, Raj, send me a paper. I would like to see that now if you have it. I would love to see a Gaussian splat Tryon paper. I know that people were using Nerf for Tryon for a bit, but it seems to have been totally subsumed by the diffusion based Tryon. I would be very interested to see Gaussian splatting based Tryon. IFTA says I am making a local first image to image search plus text to image search. Currently, I'm considering clip, VITB, and face. Do you have any suggestions? Um, as long as you're doing any kind of vectorized search IFTA, face is definitely the right library to use. Uh, pay attention to the installation. Make sure that you're using some kind of face GPU. And yeah, in terms of like the actual latency, face handles that part. So more so if you're, that's only by the way if you're going to do a vector search, which maybe that's something you should reconsider. I don't know. Anyway, clip VITB, that'll be, oh, you're saying you, oh, when you say local first, you mean you just want it to run efficiently on like consumer grade hardware, right? So that's why you're talking to me about like a VITB 32. If it's image to image, the nice thing about the clip VITB is it won't give you a 768 dim latent, right? You'll get the 512 dim latent, and that can be nice for saving a little bit of latency. And yeah, for face, it also has a CPU implementation because I'm just realizing you're saying local. So it could be the CPU, it could be the GPU. If you really want to optimize to whatever the user's architecture is, you could try to use an LLM to help you write, more specific stuff that could be optimized for like an Apple chip, or that could be optimized for something else, or maybe someone else already has, something like face, but optimized for Apple Silicon. I don't know. I'm looking for lightweight models so that even if someone does not have a GPU can also use the app. Yeah, that makes sense. I'm not sure if I know off the top of my head like the best lightweight. Oh, actually, okay, no, I do have a recommendation for you in terms of model. I'll plug my friend's model again. They get good embedding with the VIT-T, right? So you could try using the CLS token from this guy, the VITT, which should, what is the class token dim of VITT? Anybody know? What's the VITT like? Wait, was that the architecture? What's the token dim on the VITT? 192. Okay, so you could use this guy, a VITT, and like I think this frankly gives you a pretty good starting point. Like it even performs pretty well compared to like the text models, like the PE Core and the SIGLIP, even on the text tasks like the VQA. Like if we zoom in, this one is like their VITB is right here, like super competitive with the PE Core, super competitive with the SIGLIP, and those would be better than the clip. So you could use this, and you could use the VITT for a 192 dim token, which obviously, first off, that method with 6B parameters is going to give you way faster inference, and then that 192 dim token is going to be cheaper for the face lookup, right? I'll also plug myself. If you are really looking to optimize the vector search part of it, I have 8 dim tokens from this is a VITB, but it's patch size 16, unfortunately. But it gives you 8 dim tokens. So those would be pretty fast for your vector search. You could also follow the method in the paper and try to distill your own to like you could take some like SIGLIP 2 or DynaV3 and you could try to distill it into a VITT yourself and make them be smaller tokens. Or those UPay models are available on Hugging Face, right? So you could grab this UPay VITT and you could train an autoencoder that would give you even smaller latent tokens, although I don't know if you have access to enough training data to do that well. You would need like data comp or something if you really wanted it to be robust, and you would need like the GPUs that make that work, obviously. So maybe that's out of scope, but I think these are good models, especially if you're looking to go smaller and faster than the VITB. Oh, but what's the patch size? Oh, they may have used patch size 16 because that's just like modern. And that might make it be comparable in cost basically to the VITB. Just the fact that they use the smaller patch. That's kind of a bummer. Yeah, if you need patch size 32, is there anything newer or better than the clip at patch size 32? It feels like we stopped using that in the last couple of years. You could, it's kind of a hack, you could downsample the, you could compare the clip VITB 32 to something like the VITT, where you downsample the image itself to force it to have fewer patch tokens. That could work. A few different ideas for you. Okay. Let's go back to this try-on paper. I think we're done with it though, right? Because there's not, like, they're going to explain a lot about curating the data. This could be cool if you really care about try-on, but I don't think we care about try-on that much. I mean, we mainly want to see the method, and this is what we're going to get from the method. It's not much. I guess we really optimize the prompt, right? That's good to know. Like, we rewrite the prompt before we encode the prompt. Yeah. A multi-image editing DIT. I don't think there's anything crazy here, though. Okay. We made it back to daily papers. Those were all the ones I originally opened. To be fair, it was just from, like, here. Does anybody have questions for me? I'm trying to decide if I want to stay live for much longer or if I'm ready to end stream. Because this is around the time where I could consider calling it. Anyone else have a paper they really wanted me to cover from this week? I did want to see. I looked earlier this week and they weren't out yet. The conference is still happening. Is this ever going to load? Error. I guess we could have done this, right? I was waiting for, there's a place where iClear normally puts proceedings, which is, oh, they just updated the site straight up, right? Let's see, what happens when I click, okay, 2025 does this. Yeah, I was waiting for this to be populated, but it's not. I guess we could have done this though, is what I was just saying. And maybe this would have been better. And we could even shuffle by serendipity, which is kind of cool. What happens if I click that? Give me a shuffle real quick. There we go. I think since I didn't do this at the start of the stream, I think this will just be next stream. I think next stream, I need to think of a way to do it though. I need to think of a principled way to go through iClear in a stream. Feel free to suggest ideas. Oh, by the way, I meant to plug it more. We have a Discord now. If anyone in chat wants to join the Discord, the main point of the Discord is just for you to know when I'm going live. But we have a Discord. So here, let me post the link real quick to invite you to it. Anyone that's in chat right now, feel free to join. We talk about research there. Well, hypothetically, we talk about research there. Right now, it's like 5 of us, so we don't do much talking at all. But hypothetically, we talk about research. I also ping people when I go live, so you can know when I'm going live. We can do weekly papers. I mean, yeah, Raj, we can always do weekly papers, but like the weekly papers will just have the iClear from time of submission, and I kind of wanted to have a special thing to get like specifically iClear papers and only iClear papers. I guess what we can do is we could do awards. I can figure out. I don't know if they've announced awards yet. When are awards? Do y'all see awards? Do I see awards? Control F awards. Okay, they've done awards. So, ooh, okay. I'm not gonna end stream yet because I'm going to do the. Yeah, they announced this. What was it? Anyone know? Let's look at this one real quick, and then I think I'll end stream probably. Wait, they gave multiple test of time awards? Okay, cool. We can look at both. Awesome. Okay, let's do these papers, and then I think I'm good to call it for the day. Yeah. Maybe. Unless I don't know, unless something really exciting happens in chat, then maybe I'll stick around. But otherwise I'm kind of hungry. And I've been live for a couple hours. Okay, let's take a look. So these are the papers. If you don't know, if you're in the chat and you don't know what I've been yammering about with test of time, in other conferences, and iClear is doing this, I think, for the first time ever, we like to give awards for papers where who knows what we thought about them at the time, but now that 10 years have passed, it's clear that these were really important papers. Because sometimes what happens is a paper we'll get a paper, and at the time it'll seem like, wow, this is groundbreaking. But then other things happen, and it turns out actually that paper maybe even pushed us in the wrong direction, or it just isn't relevant anymore, or who knows, lots of things can happen. So we have this award, Test of Time, to recognize what are the papers that maybe deserved awards in the first place. So iClear gave 2 of them this year. One of them was for unsupervised representation learning with deep convolutional generative adversarial networks. And the other one is continuous control with deep reinforcement learning. I can understand why this paper would have been picked, because like reinforcement learning, to me personally, it felt like had like a huge boom and then a pretty big bust where some people were even willing to call it dead, followed by where we are now, which is like, to the moon basically. That first boom was when you had like Google Brain training the model to beat the best Go player in the world, win at chess, beat people at StarCraft, whatever, right? But then it felt like it wasn't quite clear how those things were going to transfer to a lot of the vision and language tasks that we were trying to solve around like 2020, 2021, 2022 maybe. And then obviously it's come back now and it's huge, and you do your GRPO or all kinds of fancy reinforcement learnings as a fine tune normally. Maybe eventually we figure out for pre-train. But for fine tuning, and that's basically, in some sense, it really did die, right? Because this was like RL as the training. We mainly use RL right now as the post-train. Maybe there will be some unification eventually. But I think it makes sense. I think I understand why they gave this test of time. This was this was not the deep Q network paper. This was deep Q learning from raw pixels, right? That's what this was. That was the key innovation, I think, with this one. Requires only straightforward actor-critic architecture, and yeah, I think the key thing here is mainly learning from pixels. Deep DPG can learn competitive policies for all of our tests using low-dimensional observations. Using the same hyperparameters. Wait. Our model-free approach. Oh, sorry. Deep DPG is their. No, Deep DPG is their approach. Okay, so their model-free approach can learn competitive policies for all of our tasks using low-dimensional observations, like Cartesian coordinates or joint angles, using the same hyperparameters and network structure. In many cases, we're also able to learn good policies directly from pixels, again, keeping hyperparameters and network structure constant. Okay. This is me trying to remember. Prior to DQN, it was generally believed that learning value functions using large nonlinear function approximators is difficult and unstable. Right, because that was the innovation of deep Q network, was like we can take an RL network and we can make it deep. So these guys did not introduce taking a deep network, taking a Q network and making it deep. That was deep Q network, but okay. Network is trained off policy with samples from a replay buffer to minimize correlation between samples. The network is trained with the target Q network to give consistent targets during temporal difference backups. In this work, we make use of the same ideas along with batch normalization. The first using batch norm, that's cool. In order to evaluate our method, they construct a variety of challenging physical control programs, blah, blah, blah. Maybe I should just look at the method a little closer. I'm trying to remember, because it's not just pixels, right? What do they mean again by the model-free approach? I'm trying to remember what that means in the scope of RL nomenclature. It is not possible to straightforwardly apply Q-learning to continuous action spaces because finding the greedy policy requires an optimization at every time step. This optimization is too slow to be practical, so instead they use the actor-critic approach based on the DPG. The DPG maintains a parameterized actor function which specifies the current policy by deterministically mapping states to a specific action, and the critic is learned using a Bellman equation as in Q-learning. The actor is updated by the following, applying the chain rule to the expected return from the start distribution J with respect to the actor parameters. I did not mean to click that. One challenge using neural networks is that most optimization algorithms assume that samples are independently identically distributed. Obviously, when the samples are generated from exploring sequentially, this assumption no longer holds. So they use a replay buffer to address these issues. Transitions are sampled from the environment according to the exploration policy, and the tuple stored in the replay buffer. And the replay buffer was full. The oldest samples were discarded. At each time step, the actor and critic are updated by sampling a mini batch uniformly from the buffer. Since it's an off-policy algorithm, the replay buffer can be large, allowing the algorithm to benefit from learning across a set of uncorrelated transitions. I don't know enough RL to know exactly how cool some of these things are. And I also don't know enough RL to know exactly how much of this approach is still used. It's also a little funny because it seems like the really groundbreaking thing was the deep Q network, right? But at the same time, it seems like the DDPG did solve some problems with the deep Q network, and it also showed that you could apply it to all kinds of inputs, low dimensional observations, raw pixel inputs. You could basically apply it to like you didn't have to do the RL, you didn't have to do anything fancy to define the state. You could literally just sample the world in like the most obvious ways. And I guess that's like the thing that makes it really helpful and makes it to where, you know, we have RL algorithms that we can use in arbitrary problems today, because you don't have to spend forever figuring out what the state is. In many cases, the state is just pixel observation. GSVTON, controllable 3D virtual triangle with Gaussian spline. Okay, I'll look at that paper in a second, Raj. Let's look at this other test of time paper, unsupervised representation learning with deep convolutional generative adversarial networks, which are DC-GANs. And this was 2016. So this is before Big BiGAN. This was before Perl, before SimClear, before Moco. Let's go look at the task real quick. Oh, actually, let's look at the architecture. Why not? Okay. DC-GAN generator used for L-Sun-Scene modeling. 100-dimensional uniform distribution Z projected to a small spatial extent convolution. Projected to a small spatial extent convolutional representation with many feature maps. So 4x4, 1024 maps. Which we progressively upsample with fractionally striated convolutions, which they're criticizing other papers for calling those deconvolutions. Then converting this high-level representation into a 64 by 64 pixel image. So we're upsampling with the convolution operation itself. So we are losing channel dimension as we upsample, because we're just choosing to have fewer output channels than we have input channels, because otherwise the complexity would explode, right? Because for this mapping, we need to have 1024 by 512 convolution layers, which is fine to do that on a 4x4. We definitely don't want to do that on a 16 by 16 or on a 32 by 32. I kind of miss old conv network design. You know, you would solve your kernel size and your stride and your padding, and in this case, the If you wanted your fractionally strided convolution, sometimes you would have like some kind of sparsity or something. Wait, fractionally strided. Wait, did they actually use fractionally strided conv? Like the stride was just less than 1? That's such a funny way to upsample. I feel like there's better ways to redesign this with like you could use like instead of a fractionally strided conv, you could just do pixel shuffle, especially because you already have this map. And so then what you would do instead of a conv that goes from 1024 to 512, you would have a 1x1 conv that goes from 1024 to 1024 or 1024 to like 2048 because then you could use like a pixel shuffle with a stride of 2 to go from the 2048 4x4 to the 512 8x8. Is that more efficient? Like, depends. It just depends. Like, if you do the kernel as a 1-dim kernel, then obviously it's more efficient, but maybe you want your kernel to be bigger. I don't know. Okay, so let's see. They obviously are doing generation, right? And they're showing us results after 1 epoch and 5 epochs. I don't know why exactly they're showing us results after 1 epochs and 5 epochs specifically. Okay, they're going to use ImageNet. They're going to give us generation results on ImageNet. They're also going to give us some classification results somewhere. Let's see. So CIFAR 10 classification with k-means and any KNN. Wait. What's a 1-layer k-means? Using our pre-trained model. Our DCGAN is not pre-trained on CIFAR 10, but on ImageNet 1K, and the features are used to classify CIFAR 10 images. So I understand when they say ours with an L2 SVM. So instead of a linear layer, because people weren't doing, were they not doing linear probe at the time? Why would this not just be a linear layer? Why would you use a support vector model for this? I don't really know, but they did. I'm trying to understand what these models are though. What is the 1-layer k-means, 3-layer k, like what is the backbone for those? Am I crazy? Let's see real quick. So a very strong baseline performance has been demonstrated from a well-tuned single-layer feature extraction pipeline using k-means as a feature learning algorithm. When using a very large amount of feature maps, this technique achieves 80.6% accuracy. Wait, is this just like literally a single linear layer on k-means pixels? In my defense, I wasn't in this field in 2016, so I'm allowed to not know some of the conventions and things that were popular at this time. Okay, so but the moral of the story is they say that these are good baselines and they can beat some of those baselines with their features from their network, pre-trained and ImageNet, and their smaller features, which I guess is fine. Where are they getting those features from, though? We should look real quick. But remember, they have this whole network. I would guess you... No, actually, I don't understand where they would get the features at all. How do they get an encoder? Do they do GAN inversion? Do people already do GAN inversion in 2016? Okay, sorry. Let's just read this. So, we use the discriminator's convolutional features from all layers, max pooling each reserved representation to produce a 4x4 spatial grid. Okay. These features are then flattened and concatenated into a 28,672 dimensional vector and regularized using an L2 SVM classifier. Okay. But wait, how did we send inputs to the DCGAN? Oh, using the discriminator? No. What? I'm so confused. I'm so confused about how the GAN extracts features. How does the GAN take input? What? Am I crazy? What the heck is this? What is it in method somewhere? I should have just read. Okay. Let's see. Okay, just check chat. The first is all the convolutional net is the all convolutional net. Blah, blah, blah. No, the second is towards eliminating fully connected. Is it just the discriminator? Is that all it is? And I'm just being like, I'm trying to find a cool thing that isn't here because obviously it's not here. Okay, it's the discriminator. Okay, I'm dumb. Well, I'm smart, but in a dumb way, where I tried to look for something that wasn't there. I'm trying to understand why this got test of time. We don't use GANs anymore. We barely use adversarial learning. You can use it if like you're trying to do low steps diffusion or something and you just are desperate to try to bump the quality a little bit. We definitely don't use GANs for unsupervised learning. Like Big ByGAN advanced this quite a bit, but even that Big ByGAN idea is dead. You know, take the discriminator of our GAN and use it as a feature encoder for ImageNet. At one point, that was the state of the art for representation learning, but that was a long time ago. So yeah, I can't really fathom. Maybe if I was there at the time, I would have a little bit better of an understanding of how this was advancing the field at the time. Like maybe there's a lot of work that we did that we wouldn't have done without this. And I suppose it is nice as like an early paper to show like something happening in like unified training, right? Where like a generative training can help a discriminative training, right? Because the GAN training is like the main purpose of us doing it is that we're generating, but we do train a discriminator, and that discriminator learns to generate useful features. So I guess that's good. Anyway, those are my best guesses. Let's see, GSVTON, controllable 3D Tryon, Gaussian. Okay, yep, it's populating. I don't know Gaussian splatting too well, just as a heads up before we even get into it, so this might be mostly me learning, but that's fine. Okay, controllable 3D virtual Tryon with Gaussian splatting. So text prompts cannot provide sufficient details in describing clothing. 2D virtual Tryon results generated from different viewpoints of the same 3D scene are not often coherent and they lack the spatial relationships. So there will be appearance inconsistencies, geometric distortions. So they have an image prompted 3D virtual Tryon, which leverages 3D Gaussian splatting as a 3D representation, enables the transfer of pre-trained knowledge from 2D to 3D while improving cross-view consistency. So they propose a personalized diffusion model that utilizes low-rank adaptation to fine-tuning to incorporate personalized information into pre-trained 2D VTOM models. They propose a persona-aware 3DGS editing framework to facilitate effective editing while maintaining consistent cross-view consistency. And finally, they establish a new benchmark. Okay, so they're going to try to put 3D priors into the 2D model, but then they're going to do some final thing with the 3D model using multiple 2D views. Is that what I'm understanding? I can't really see that diagram good enough to get that here. And I don't have any results yet, so I'm not sure if I'm willing to say this works. Sorry, these like very results heavy papers where it's like I have to look at the images, I think, also very hard to answer in 1 minute. But let's try not to spend too much more time here. Let's see the pipeline where okay, so we introduced reference-driven image editing method that facilitates consistent multi-view edits. Okay, so we're going to get multiple views and a clothing image, and then generate all the edited images. With the edited images, we can then train a personalized diffusion model with LoRa fine-tuning. Is that going to be like personalized to like the specific clothing person pair? And then what's the 3DGS part of it? So the core of their network is a persona-aware 3DGS editing, which by leveraging the personalized diffusion model respects two predicted attention features, one for editing and the other for ensuring coherence across different viewpoints, allowing for multi-view consistent 3D virtual Tryon. So, whoa. Sorry, I'm trying to make sense of this diagram. I'm not really sure where to start with it, honestly. We have our source image here, okay? Source image. And then I have my personalized diffusion model, which can predict the edited image. Why does ControlNet not show up in either of these, but it does show up here? But anyway, we're using ControlNet to help us do it. Fine. Where do we get the parsing map from? Random mask, I understood. Where is parsing map? How do we get that? But then we do this diffusion edit process to get the edited image. Oh, I think what I'm seeing here is that I have all these input images. I can use them to learn a Gaussian splat. From that Gaussian splat, I can render arbitrary images. And then, is Gaussian splatting invertible? Like, since these are the same view, can I just invert it to go back? And like, I'm just updating the pixels in the Gaussian primitive, basically, like the color parts. Is that how I can do this? So I just update the Gaussian splatting according to what came out of here. And then, this is the part I'm really not understanding. These are just Gaussian splat preliminaries, right? Which I maybe should look up, but really don't want to. Building on instruct pix to pix and 3D-GS, IG2G. Oh, so this is a prior work. Facilitates text-guided scene editing with a given 3D-GS model and its associated training data set. What is it achieved in two main steps? For a rendered image from a specific camera viewpoint, it first introduces Gaussian noise to the image. This noisy image, alongside the text embedding and the original training image, serves as conditions for instruct pix to pix to generate an edited image. Okay, so we have a rendered image and then an edit of that rendered image. These changes will then be back propagated to the 3D-GS scene to update it accordingly. Okay, so I think the part that I'm missing is that if you update any of the images, since you know this render process, you can just reverse it. Is that what's happening? I guess. Because this is just a primitive to pixel mapping, so I also have a pixel to primitive mapping, and I can update the primitives if I just know what I updated in the original image. Is that what's happening? Regardless, it seems like the right high-level thing to say here is we can use the model to generate edited images, which we use to update the Gaussian splatting representation. And it looks like they're saying they don't even do anything novel there. That just comes from instruct G to G. Except they take IG to G, which is for text-guided scene editing, and they adapt it basically to this personalized clothing trial with personalized diffusion model with LoRa fine-tune. So they take the IG to G, and they adapt it for clothing. How are the results? Oh, I was already zoomed in. Yeah, thanks, Raj. Yeah, it looks like the 3D-GS stuff is just prior work, and their part is the personalized LoRa diffusion that they plug into that framework. Right? I'm understanding properly, Raj, I think. No, that's just some ablation. I actually don't care about that. I mainly want to see where they compare it to prior works. Okay, are these okay, sweet. So, oh, apparently these are well, this is them comparing to other 3D scene editing techniques, which I mainly care about how they compare to clothing try-on. But I'm not really getting that, right? I'm not seeing comparisons to like state-of-the-art clothing try-on. I'm seeing comparisons to like other Gaussian scene editing, which seems pretty weird. Is this Vika Nerf at least a clothing try-on? No, it's just scene editing. What the heck? Virtual try-on existed before this paper. Why were you not comparing to any virtual try-on stuffs? Am I crazy? Am I missing that? Is that not here? Or is it here and I'm just blind? I don't see it. I see gosh, I see all these 3D scene editing. I see baseline. Here, maybe the baseline is the baseline method generates edited training image set individually by IDM VTON. Okay, sure. Okay, cool. So that's this we get some baseline comparison. Let's check it out. I'm not sure if this is a great baseline, but okay, I don't think so. This paper did not invent virtual clothing try-on. And this baseline is failing to do the color even. So I don't know. I wish I could see more timely, like the actual correct baselines. Oh well. Okay. I've been live for 2.5 hours. I had a good time. I hope y'all had a good time. I think that's it for me for today. I went live for one bonus stream last week. I hope to do a similar thing this week, probably like Pacific time around 9 p.m. or so some night, 9 p.m., 10 p.m., somewhere in there, randomly. If you want to know when that happens, I'll post my Discord link one more time. Feel free to join the Discord. Would love to have you there, and thanks for watching. See you next time. Bye.